Good morning to all of you. Welcome to the DMT workshop. Actually, it's a workshop on the flat dilatometer, the seismic dilatometer, and the Medusa DMT, which is a fully automated dilatometer. I would like to thank the organizing committee for allowing for this workshop to work, even with all the difficulties of the pandemic and with this excellent team of IT technology. Thank you for your help. The program of the course today is, it looks very long, between 9 and 4, but it's not that much, considering that we have two coffee breaks and one free time for lunch. It was not possible to organize lunch here, so for those of you who will attend, there will be a break between 12:30 and 4, and then 14, which is 2 p.m. So that we can have a lunch and then we will come back. The first presentation is delivered by myself. It's going to be an introduction to the equipment, the DMT, the SDMT, and the Medusa DMT. So it will be mainly on the equipment, the test procedures, and the interpretation of the results. Then, after the coffee break, we will have Paola Monaco, who will give, she is from the University of L'Aquila, a full-time professor, and she worked a lot with Professor Marchetti, so she is established a team with us in the workshop and also with Professor Marchetti in the past. And she will talk about the applications of the DMT and the SDMT. Starting from the results that I will have shown in the first presentation, you will see the main applications for which this tool, the DMT, is used in the world, with some updates compared to the latest researchers and publications. Then we will have the free time for lunch, 1 hour and a half, and then there will be Professor Sara Amoroso from the University of Chieti. She will provide in these two time frames, divided by a coffee break, some specific applications that were explained by Paola Monaco, but with in specific projects like case histories. So it's in my opinion very useful, because you can see today the whole path from what is the equipment, how to use the data, how to obtain the interpretation, what applications you can do, and for the ones that Sara Amoroso will do, really some examples, which are useful then if you have a similar case. Okay, so let us begin. I like to show this slide. Professor Marchetti is the inventor of the flat dilatometer. He was born in 1943 and passed away in 2016. After many years of research, he invented the flat dilatometer in its first version in 1974. And only in 1980, it started to be distributed in the world. Now it's used in over 80 countries. So if we have this workshop today, it's because of this man here. Now, we all know that in the last years, there has been a long migration from laboratory testing to direct push technology in penetrable soils. So where it is possible to push testing equipment. And in particular, the two most used tests in the world are the CPT, or seismic CPT, and the DMT, or seismic DMT, that you see in this picture. The reason is that with this direct push technology, meaning that with a penetrometer we push the equipment in, it is very simple to do the test. It is fast, repeatable. It provides a continuous soil profile compared to laboratory tests where we have points that may be very far away, and the results are available real time. Particularly in sands, it is sometimes impossible to obtain undisturbed samples. So direct push technology is the state of practice. In this presentation, we will focus on the SDMT, because this is our area of expertise. And normally at these conferences, there were also workshops on the CPTs, but I think not this year. So the seismic dilatometer is the combination of the flat dilatometer, the one that I told you was invented by Professor Marchetti in 1974. And it was then completed and updated with the seismic part, which is an instrument behind the blade that we will see during this presentation. They are combined so that when you do a sounding, you can do both tests in the same sounding. Now, the test consists of using a standard steel plate or blade with a membrane on one side. It is pushed into the soil using penetration rods, steel rods. A pneumatic electric cable runs from the control unit inside the rods down to the blade. This is a pneumatic and electric cable. We will see why. A control unit is required to operate with valves and for measuring the pressure. A gas tank for providing the pressure source, and a penetration machine, which is this black arrow for pushing the equipment in the ground. The computer is used for the data acquisition of the pressures, which first were recorded manually when performing the test, and now it is possible to acquire them directly in the computer and to see the results during the test execution. The measurements consist in advancing the blade starting from the plane of the ground, from the ground level, and advancing every 20 centimeters and stopping. Initially, the pressure of the soil will flatten the membrane against the blade, and the operator will start to inflate the gas that will start to counterbalance the pressure of the soil. When the pressure of the gas is in equilibrium with the total horizontal stress against the membrane, it will start to expand. So this instant, the A pressure reading is obtained. It's also called lift-off pressure because the membrane lifts off from the plane where it was flattened by the soil initially. The operator does not stop, but continues to inflate the gas. The membrane will expand. And when the center has expanded 1.1 millimeter, the second pressure reading, B, is obtained. So the B reading is the pressure that was necessary for expanding the membrane in its center of 1.1 millimeter. Then the operator has to deflate after B. If not, the membrane will become like a balloon and will not be good for the next measurements. And if the deflation is fast, only the A and B readings are taken. If he will use a special valve on the box, which is for a slow deflation, the membrane will return in its initial position. And when it has flattened again in the original position, the C reading is obtained. The C reading, I will talk about it later during interpretation of the results, is important in sands because it measures the water pressure, but only in sands, not in clays. Just to show the test sequence, once we have advanced the blade at depth, as I said, the pressure of the soil, which is represented by the red arrows against the membrane, will flatten the membrane and the contact of the audio signal of the blade will be on. Then the operator will start to inflate. And when the pressure of the gas, which is the blue arrows, is exactly the same as the pressure of the soil, a total pressure of the soil in the horizontal direction, the membrane will move, expand, and the signal will go off and the A reading will be taken. The operator will continue to inflate from step 2 to step 3. And when the membrane has expanded 1.1 millimeter, the contact will come back on because inside the blade, there is a mechanism who will give this contact again. And so the B reading is obtained. Then he will deflate, the signal will go back to off. And when it returns back to on, it means that the membrane is flat. And that is when you take the C reading, if you deflated. This is the control unit, the new one that has been supplied since a few years. The old one was with much bigger pressure gauges, but did not have the automatic acquisition of the data, which are the parts that you see on the right side, the USB going to the computer. You still have the pressure gauges, because in some circumstances you may be interested to take the measurements manually and to write down the readings that you take by looking at these gauges and with the audio signal represented by this buzzer. But now today everyone prefers to do it with the automatic acquisition. These are the valves of the control unit, the connections to the blade. I'm not going to go into details, because if we have to look at all the details, it will be the training of the equipment. Here we are doing a short course to give a general idea of the DMT. But this was the valve I told you for the C reading, to deflate slowly after the expansion to B. And this is the fast vent valve if you don't do the C reading and you just deflate. And this is the flow valve to pressurize. So these are the three main valves that are used during the tests. You still have to use the valves even with the automatic acquisition of the data, because you have to inflate and deflate. But instead of reading as in the past and writing down the readings, they will be visualized on the screen and the readings taken automatically. So the blade is a stainless steel blade with a flexible membrane mounted on one of its sides. The diameter of the membrane is 60 millimeters, and this is a picture of the membrane so that you can see the shape and the consistency of the part. Now, this is a new slide I am showing for the first time because it concerns the membranes and the different thicknesses of the membranes. There are membranes of 0.20 thickness, 0.25, and 0.30 millimeter. In the beginning, when Professor Marchetti invented this equipment, the membrane were of 0.15 millimeter thickness, so even thinner. Now, it is very important to understand that the membranes are not the measuring system. They are not a transducer. They are simply a separator of the soil and the gas or the fluid with which you are inflating the pressure. So it's not the measuring device. The accuracy of the test data is the measurement of the pressure of the fluid, okay? So this is why it is possible to change membrane and to have the same results, because you want to use softer membranes, perhaps in soft geomaterials, because if you use a very thick membrane, the pressure of the soil may be so weak it will not even close the membrane, especially in the soft part at the surface. So you would like to use these 0.20 only when you are in soft soils with the pneumatic equipment. The standard membranes are 0.25 millimeter thickness, and the thicker membranes are 0.30 that you maybe want to use when you are in dense sand. Maybe you have some gravel, something that can cut your membrane and you don't want to interrupt the test. So these are the indications of what type of soils to use with the pneumatic DMT equipment. With the Medusa, it is we have experienced all of them, and we have understood that since it's fully automated and it can go in suction with extremely high accuracy, we use always the 0.30 because we have the same accuracy with the others of the other thicknesses, but we have the resistance in a very dense materials and also with gravel. So with the Medusa, we don't need to change the membrane because we don't have any particular gain in accuracy. While with the pneumatic, we do. Now, the membrane calibration is something that we have to do to account for the membrane, because not only they can be of different thicknesses, but the membrane itself, whatever it is, has its own rigidity. And when we measure the soil, we don't want to interfere our measurements with the rigidity of the membrane. So the target of the membrane calibration is to account for its rigidity. I don't like the term calibration because calibration, it looks like you can do some tuning on the membrane. It's not true. It's like a tear. When you go to buy food, you weigh the container and the food, and you subtract. So that is the same principle here. You want to measure the stiffness of this membrane, and then you subtract it to the readings in the soil, which are soil and stiffness of the membrane. When we do the membrane calibration, we have to have the blade outside of the soil in free air. And in free air, the membrane will be in the dashed dotted line, meaning that it will not be flat in the A position because no one is pushing it. It will not be expanded in the B position because no one is inflating it. So it will be in the intermediate. The calibration constants are defined as delta A and delta B. Delta A is the external pressure we have to apply on the membrane, like if we start to press it with our hand, in order to position the membrane and flatten it in the A position. The delta B is instead defined as the internal pressure that we have to apply to expand the membrane from free air to the B position. Basically, they are A and B readings made in the air so that they can be subtracted from the ones in the soil. The only problem is that in the air, the membrane, it's actually a negative pressure because the membrane is in the middle, while when you're in the soil, the membrane is always closed. So A will be positive. These are the tools that you need to use to perform the membrane calibration with the pneumatic equipment. A short calibration cable, because if you use a long cable when you try to do suction, you will not be able to do it. A syringe to do the suction and also for pushing to obtain delta B. And of course, the control unit. And if you have the computer and the acquisition, of course, you can connect it. The procedure for performing the delta A calibration is very simple. You have to apply abundant vacuum by pulling the syringe back so that the vacuum will cause an inward deflection of the membrane, similar to the soil pressing against the membrane, and so the buzzer will be on. And then you slowly release the syringe. The pressure will, from negative, become closer to the positive, to zero. It will increase. And delta A is the pressure when the buzzer goes from on to off. That means when the membrane will start to expand. It will be a negative pressure because it's a suction, but it's conventionally taken as a positive number for how it was defined in the formula. It's just a convention. Now, for delta B, it's much simpler. You simply have to apply a positive pressure by pushing the syringe. Initially, the contact will be off because there's no contact with the blade. And when it has expanded 1.1 millimeter, the signal will go from off to on. And that is delta B. It's good practice to repeat delta A and delta B until the values are stable. Now, delta A and delta B are used to correct all the A, B, and C readings to obtain P0, P1, and P2, which are the corrected readings corresponding to A, B, and C, once we have eliminated the rigidity of the membrane that we talked about before. Delta A and delta B must always be measured before and after a complete DMT sounding with the blade out of the ground. The calibration is a good indicator of the equipment condition. If your calibration constants are in the range that I will show you in the next slides, it means that the equipment is in good shape. If not, there could be a problem in the instrumentation. If there is a large difference between before and after delta A and delta B values, generally it is apparent and you have to change the membrane. Now, the acceptance values of delta A and delta B for the Eurocode are for delta A in the range between 5 and 30 kPa and delta B between 5 and 80 kPa. When these standards were written, the first time, they were for the membranes of 0.15 and 0.20 millimeter thicknesses. Then we went to 0.25, and these ranges are still okay. But now that we have 0.30, the resistant ones, the ranges are these ones. I'm trying to get them in the standards, but it takes a lot of time. So I am saying it when we do the training to the people using the equipment, that the 0.30 has a delta B that is higher, while the delta A is perfectly in the range. If the values of delta A and delta B are not in these ranges, you have to replace the membrane. It could be damage the membrane or some other problem in the blade. I will not go in the details of course, of how to do the maintenance of the blade, but that is part of the technical training of the equipment. The final value, this is important, the final values of delta A and delta B should be with a change that must be less than 25 kPa. So if either delta A or delta B between the initial and final values at the end of the test of the full sounding have changed of more than 25 kPa, then it means that the membrane is not good and the test should be discarded. However, let me say that the standard, which is very rigid, there are some exceptions. Suppose you do a test in a very soft soil. Everything is perfect. You have good calibration values at the beginning. You do a test, and then there is a very strong material, perhaps even a gravel. You try to penetrate just to get a few readings, and you break the membrane, or the membrane breaks. When you get it out of the ground, the values will be different, or you may not even be able to do the calibration because the membrane is broken. So in that case, you know that the values, you will take the initial values up to that depth, and then you cannot do the final values, but you're not going to throw away the data because you ruined the membrane at the last measurement. So of course, always keep the brain switched on to understand these cases and the rigidity of the codes. Excuse me. Accurate delta A and delta B values are extremely important in soft soils, such as nearly liquid clays or liquefiable sands. Why? Because the readings that you take in the very soft materials are only a small, are of the same order of magnitude of delta A and delta B. It's the concept of percentage error. So you really want to be extremely accurate in the calibrations and also in the measurement, because there will be a subtraction between the two, and any small mistake will be big. If you are in a medium to stiff soils, you still want to be accurate in delta A and delta B, but they are a small portion of the readings, A and B, a small percentage, so the error will be small. These are examples and pictures of the pneumatic electric cables. They are pneumatic because in this nylon tube, the gas will flow. They are electric because inside there is a steel wire that brings that famous contact I'm talking about on or off for the contact of the membrane. It's just an electric signal, not an electrical or analogic signal. It's just like a switch, on or off, membrane contact or no membrane contact. So it's very simple, very robust, and it works well even mechanically. These are non-extendable cables. So you connect to the blade and then to the control unit. These are extendable cables, meaning that you can connect them and extend them. Now, even if you have to go very deep, this is really important. Never combine the cables immediately if you have to go to like 80 meters. You first start with an extendable cable. You do the test. When you arrive at, if this is 30 meters, when you arrive at 30, after you add another cable. If you start at the surface with combining two cables, for example, 30 plus 25 plus 34, 59 meters, because you have to go deep, you will be inaccurate because you have a large capacity in the whole cables, and maybe in the first meter it's very soft material, and you will read on your box a certain pressure. By the time it gets that depth, it's different, and even a small mistake in soft soil may be a large error in the interpretation. So to conclude my suggestion, when you have to combine cables, you always start only with one cable and then you add them later on. You can add them only if you use the extendable cables. Once you put a non-extendable cable, you cannot extend this joint anymore. this is the summary of when you do the test with the acquisition system and the software. This is the new software we are proposing. You see the pressure gauge, the digital pressure gauge here, and basically the test of the DMT consists in getting two numbers, A and B, and sometimes a C reading every meter. It's not worth to do the C reading always, but we will talk about the C reading later on. Now, another tip I want to show in this training, because many users do not pay attention to it, but it's important, is the inflation rate. It is written in the Eurocode and in all the international standards of this testing. The inflation should start as soon as penetration stops. So we said that every 20 centimeters we push and we do the inflation and take the readings. So if we indicate as T0 equals 0 when we stop penetration, you immediately start to inflate. Then the inflation time should be done so that the A reading is taken in about 15 seconds. Plus or minus 5 seconds is okay. But you don't want to take 2 seconds because you go really fast and you inflate immediately. And you would be very inaccurate in the pressure. You don't want to take 3 minutes to take the A reading, because then the soil will dissipate and the readings will be completely wrong. So it's important to note this timing of the readings. And also for the B, when you inflate from A, which is the first reading, to B, you should take about 15 seconds again, plus or minus 5 seconds. Let me tell you that even if it's plus or minus 7 seconds, it's okay, but don't take 3 minutes or 2 seconds, as I said before. The reason is to limit also the pressure differences between the pressure at the opposite ends of the cable, and also for the validity of the correlations proposed by Professor Marchetti, which are with these timings. All the correlations were done with this rule. Now let's look at the seismic equipment behind the blade. It is possible to connect an instrumented rod with two sensors, a top sensor and a bottom sensor, and an electronic board inside the tube. The test consists in generating a shear wave with a source that is generally composed of a hammer and a plate, or shear beam, it's called. It must be well pressed vertically in order to provide correct coupling and good coupling with the soil. When the hammer hits the plate, the particles of the soil will move in this direction, in the horizontal direction. The shear wave will propagate in the vertical direction and arrive to the top and to the bottom sensor. The electronic board will record, will amplify and digitize the signals, send them at surface through the wires, and you will see the two waves that were recorded. The system will automatically and real time evaluate the delay in the wave arrival, delta t, with the geometry, because he knows the depth. It is known the depth of the blade and of the sensors, and with the distance of the hammer to the rods, he will evaluate S2 and S1 and obtain the shear wave velocity and propose it to you. From that, it is easy to obtain with the well-known formula G0, or the maximum shear modulus, using the soil density and Vs squared, which is obtained this way. Now, let me show you a few tips on the shear beam, because it is really important to obtain high quality seismograms or waves, and also for enabling the automatic interpretation real time of the shear wave. In this picture, we see three really important points of the hammer. First of all, if there is pavement on the soil, in the area where you have to test, you have to remove the pavement. If you put the shear beam on a pavement, when you hit with the hammer, you will generate the vibrations, but they will go in the pavement everywhere, but they will not go in depth, because it tends to go in the rigid and lose all its energy. So remove the pavement if it's there, if necessary, because the pavement is maybe 30 centimeters thick. Once you removed it, you can fill it in back with gravel, with sand, or with what you want, so that the level is up. You can't have your hammer down. It's practically impossible to hit if this is below the level of 0.5 meters. So you can. Maybe you want to remove big pieces of cobbles because they can generate impurities in the waveforms. But gravel is okay. The second really important point is that you want to apply a strong load on the beam. This is really important, especially if you want to go very deep. But in general, if you want good waves, it's better to apply the load. You cannot, you don't have any negatives, any cons if you apply load. You can only get benefits. And the idea is to push vertically against the plate so that you have a very good coupling with the soil. And when you hit horizontally, you will shake the soil below the plate. And that's what you want for obtaining a very good shear wave. The third and most important point, if you're using the load, is to put the rubber. The rubber is really important because when you apply a load, you make a connection, a rigid connection between the load and the plate. So if you hit the hammer horizontally and you don't have the rubber, the vibration will go in the truck. In the beginning, we did this, and who was in the truck every time was shaky. So, and no, the wave was not good at depth. So then we put some rollers at the beginning, but they're difficult to put. So we found that with the rubber, a lot of rubber, you have an excellent transmission of the vertical load and completely decoupling the horizontal vibration, and it works really well. So this is important to get good seismic waves, good shear waves, and to enable the interpretation of the shear wave velocity real time. These are the shear beams we supply. We don't supply the hammers because it's more expensive to ship them than to buy them. But we provide the plates because they have several details, including these sectors that you see under each of them. They are really important because when you press them, they grab a big bulb. And when you hit with the hammer, you shake very well the soil and you get a beautiful wave. If you don't have these, your wave, your beam will slowly move, and the wave will not be as good, as clear as when you have them. This is the standard seismic combination that we suggest when you're up to 25-30 meters. A hammerhead of 2 kilograms is okay, even though we suggest more. The more, the better in general. You can always hit not hard, but if you have a very small hammer compared to the weight of the beam, your hammer will bounce back and you will not get a good wave in the soil. This is the larger plate that we suggest for at least 30 meters when you want to go 40, 50, and a strong hammer that you can buy in any shop, at least 5 kilograms or more. This is the new software as DMT Pro that we are suggesting as an improvement of the previous. In this case, you have all the data that is here. In particular, one of the things we have done is that you can combine the seismic equipment with the blade, with a dummy cone tip that we can provide, or also with CPT, because we have combined our seismic system with CPT manufacturers from Holland and also from Italy. And this way you can use our seismic system and the CPT also, not only with the flat dilatometer. So you have the depth of the blade, of the tip, let it be the blade, the CPT, or dummy cone tip. And you can save the repeatability values of the shear wave if you record more than a few blows with the variation coefficient, so you know how repeatable is your measurement, the depth of the center of the sensors and of each sensor. And these are the amplification of the signal at depth, the sample time, the number of samples recorded for the wave, and the distance of the hammer and the trigger. I don't want to go into details because it would be the training of the equipment, and we don't have time to look at all of these issues. So when you click on acquisition, you will be prompted to energize. That means to hit with the hammer and generate the shear wave. And immediately after a few seconds, you will see the results. So you will see the wave recorded, the wave as recorded, and you see that the blue is the top sensor and the red the bottom, and there is a delay in the arrival. The algorithm inside the software will evaluate this delay between the blue and the red and give you an immediate interpretation of Vs, 216 meters per second, and will show you also the rephased signals, which means, look, I evaluated this delay to give you Vs, and I rephased the red backwards towards the blue of that delay, so that you can see that you have a good superimposition of the wave. Just a note, the importance of the superimposition is not in the amplitude, because the wave can decrease in amplitude from the lower sensor and the top. It's only the phase that you're interested, if it's delayed or not. So what you want in general are the peaks are in the same time, and the crossings for the zero are in the same position. So this shows you that you have a good superimposition and a good quality of your waves. And of course, you want to have a good repeatability, which means a low variation coefficient, which means that your values are pretty much the same, repeating the measurements at the same depth. Now, the main features of this system is that the execution of the test is very fast, because you don't have to pre-drill with a borehole if the soil is penetrable. You don't have to wait for the cementation of the hole like you have to do for a crosshole and downhole. The evaluation of the shear wave is automatic. The system will evaluate the delay time for you, and if the waves are clean, like they are if you follow the recommendations that we provide in the training, you don't need the post-processing, almost never. It therefore is operator independent and provides the results in the profiles real time. A very important point is why there is such a high accuracy in delta T with these systems. Because of course, the electronics is a very high quality and custom designed for the acquisition of these sensors. The signals are amplified and digitized at depth. There are still analog systems that have the sensors at depth and bring the analog signals at surface. You see the signal can be very small when you're deep. And once it goes out of the rods where it is protected because it's good electrical ground, it can capture the noises at surface. So it's important to have a digital system so that once you send the data above, it cannot get corrupted. And maybe the most important point is the true interval. True interval means that you have two sensors instead of only one. Many producers say, oh, I want to put only one sensor because then my probe is too long. And when I ship it, it's difficult to ship because I want it short. Okay, but well, then your accuracy decreases. Why? Suppose you have only the top sensor. You have to do the measurement, you record the wave. Then you have to go, for example, half a meter below, because these are spaced half a meter or 1 meter. And you can make even a small mistake. Instead of half a meter, maybe 50.1. That's a mistake. Instead, if you are exactly built with a fixed distance of 50, you cannot make that mistake. Then you have to give a hammer blow when your sensor is at this depth, and then when it is at the other depth. And it's very difficult to give the same hammer blow at two different depths, because inevitably you don't hit in the same place, you don't give it with the same intensity. So it can provide inaccuracies, small inaccuracies, but big in the interpretation. And also the trigger can trigger a little bit before or later. So there is no chance that with only one sensor, you can get more accurate result with two. So don't consider ever to use a system with only one sensor. There are many producers now who do with two sensors because they understood this. So just don't get the old ones with one sensor. Now the SDMT, under pressure of users of the SDMT who use the CPT, we have combined in cooperation with CPT constructors, the SDMT cone. sometimes called the S-seismic CPT, but this SDMT cone, it means it has the SDMT on it. Currently, there are three partners, Gouda Geo from Holland, Geomil from Holland, and Pagani, and probably Vanderberg. We are talking with them to put the SDMT on their CPT so that you can use in the same sounding, do both tests. Anyway, any other CPT system may be combined because it's only a matter of passing the wires of the CPT inside this tube and here make a joint of a single cable going upwards. Now, let's look at the penetration machines that can be used to advance the DMT and the SDMT equipment. The most effective and productive way of performing DMT measurements and also CPT is to push with heavy truck penetrometers because they're able to push up to 20, 25 tons or even 30 in some really particular cases without lateral instability because they have their weight reaction. You can push 20 tons even with these small rigs. This is a Pagani rig and an Italian constructor. Many of our DMT users use this penetrometer because it's less expensive, it's easy to transport. The problem is that when you push, even with pistons that could push 30 tons, it will go up unless it is able to anchor very well. So in soils where the anchoring works, I'm not an expert of anchoring, but you can put the anchors and you get the reaction from the soil and you can push up to 10, 15 tons. But when it's not so easy and it's also a little bit time consuming, then the machine will go up and you cannot push that much. There are many other machines you can use for the DMT and SDMT because the DMT performs the measurement not during penetration like the CPT, but only when the blade is not moving. So it's not interested, the instrument, how you put it at depth. You can push it, you can drive it, you can use a light penetrometer for static and dynamic, or from the bottom of a borehole, push it. So indeed, you have to just get the instrument in the virgin soil for 20 centimeters, 40, 60, and you can do your measurements. Let me show you a detail of this torpedo method, because if you need to use a drill rig, this is the way to go. There is a top adapter that connects to the drill rods that are generally 76 millimeter diameter rods. And this adapter is done so that the cable of the pneumatic electric cable passes in the hole of this adapter inside. And this system is pre-assembled before starting the test. You then drill a hole at a certain depth. You connect the torpedo to the drill rods. So here you have your drill machine, which pushes, not rotates, just pushes from the bottom of the borehole the system. The cable is taped to the rods and goes to the acquisition system. So you lower the system to the bottom of the borehole and you push every 20 centimeters and do the test. Once you are finished with the length of this torpedo, which is 3 meters or 5 meters long, then you have to stop, because then you would break the cable. If this cable arrives at the bottom of the borehole, you will cut it and pull it back out and drill again and repeat the operations. Of course, it's much slower than with the penetrometer, because with the penetrometer, you just push up to 40 meters and then you extract. Here, you have to alternate the drilling and the measurements from the bottom of the borehole. So you take about 40 meters in one day, you can obtain. And the good thing, however, of this system is that if you find layers that you cannot penetrate, you simply drill them and then continue below. So virtually, you can go to the center of the earth if you have a lot of time. The DMT and SDMT was used also offshore, in this case using a drill rig from a floating barge, but we have done several combinations. I had a presentation on the offshore test, but we don't have time to look at it. You may find publications in literature. I like to show this because it's with a drill machine on a floating barge with the SDMT. And this is a hammer that we have designed for generating the waves from the lake floor in this case, because this is a lake. And with a pendulum hammer, you generate the waves and you measure, of course, with the SDMT. In this case, we went up to 50 meters of water, and we had to hold the hammer because the rods would, if not, fall down, but it worked very well with very regular waves. What are the scope, the ranges in which you can use the DMT and the SDMT? Well, the DMT can be used in all penetrable sands, silts, and clays where the grain size of the material are small compared to the membrane diameter of 60 millimeters. You cannot go in gravel because you would break the membrane, even though it's not expensive, but you would lose a lot of time to extract and put a new blade or replace the membrane. You cannot go in rock because even if the blade is robust, it doesn't make sense to do this test in rock. The pressure is not representative of the rock. So only materials up to sands, coarse sands, or even with a little bit of gravel. But if it's only gravel, don't do this test. You will suffer a lot. This means that you can go from very soft soils with values of strength very low and modulus also very low to hard soils, almost soft rock, with values of undrained shear strength and modulus of these that you see on the screen. The blade is very robust and it can withstand a safe push up to 25 tons. Generally, if something breaks, it's the rods, it's not the blade. The SDMT can be performed behind the blade in all penetrable sands, silts, and clays, but it can also be performed in non-penetrable soils like gravel, very dense sand that you cannot penetrate. In this case, you have to drill a borehole. I'm not going to show all the details. There are papers and we can provide you with the procedures. This is the paper, and there are other papers that you can find on our website. You have to drill a hole, fill it with gravel, rounded gravel, and then push as if it was a penetrable soil. And you would obtain values of VS that are valid. And this is explained very well in the paper, but I don't have time to show that in detail. The max depth that we have done until now for seismic measurements is in L'Aquila after the earthquake for measurements. And we went up to 135 meters. So this is a good record. Now let's look at the interpretation of the DMT results. We said that we go in the field and we take two pressure readings, A, B, and eventually the C reading. But what do we do with these pressure readings if we want to provide the results? Now, the first step is to correct the readings. I already showed you this, A, B, and C, with the calibration constants, delta A and delta B, that are somehow subtracted to the readings. You get the purified or corrected readings. A is P0, B is P1, and C is P2. Now, the most important step is really this one, the evaluation of the intermediate parameters. From P0, P1, and P2, through definitions, not correlations, definitions, you obtain 4 intermediate parameters, ID, KD, ED, and UD, that we will see in the next slides. The first one gives you information on the soil type, material index. The second one on the stress history or the horizontal stress, which is really precious for many applications. The dilatometer modulus, which is related to the expansion of the membrane, and the pore pressure index, which is related to the C reading or P2. Now, these have a specific meaning that we will see in the next slides. Sorry. And sorry, I did not, I'm missing a slide. The last step is to obtain the geotechnical parameters that you see here, the unit weight, the horizontal earth pressure coefficient, OCR, undrained shear strength, the modulus, friction angle, and so on, as a combination of the intermediate parameters, ID, KD, ED, and UD. So I'm not going to go through this. I just want you to understand the structure. Field readings, the A, B, and C readings, and the calibration. This is of the dissipation test that I will talk about later, but these are the field readings. Then corrected readings with the calibration to eliminate the membrane rigidity. The intermediate parameters, ID, KD, ED, UD, and for the dissipation, the flex point, and then the interpreted geotechnical parameters. It's really important to understand these steps because it's how the Professor Marchetti created this framework for the interpretation to the geotechnical parameters in 1980, and today it is still used as it is. There are so many publications showing that, especially the modulus and drain shear strength, calculated with this formula that he found in 1980, are still working very well and have received very minimal corrections in soils that are maybe very, very complex or different, but in 90% of the soils, they are valid. So I think this is important to point out. On the right, you see the soil behavior type chart where you enter ID, which is one of the intermediate parameters, and ED, which is the other intermediate parameters. So at every depth, you have ID and ED, and you go into this chart. The software does it for you. And he tells you if you're in clay, silty clay, silt or silty sand, and so on. And this number you see in the box is the unit weight of the soil estimated from the DMT. So 2.1 means that the unit weight at that depth is 2.1 times the unit weight of water. This is the new software that we are proposing as DMT Pro, which tries also to present the data with this format. Before it was a little bit mixed, the field data, the intermediate parameters, and the interpretation. Now they're very well separated, like I show you here in the slide before. But we will see during this presentation many graphs with this new software. Now let's look at the intermediate parameters to understand what is their meaning in terms of soil parameters. If we do a test with the DMT, we will immediately notice that the two readings, corrected readings, A and B, or P0 and P1, are very close to each other in clay. When you are in sand, the second pressure reading is at least 2.5 times the first. And of course, the silt is somewhere in between. So ID is defined as P1 minus P0 divided by a normalization factor, P0 minus U0. So basically, it's the difference between the readings. Just to show you an example, this is a test site where there is an alternation of sand and clay. Look, in sands, we see values like 2.6 and 11.9, a ratio of about 4 to 5, indicating that you are in sand. Whereas in clay, in this case, about 19 meters, 20, or in this area here, you have readings like 5.8 and 6.65. So a ratio about 1.1, 1.2. So it's a very clear distinction between the two. And of course, the silt falls somewhere in between. The second and most important parameter, intermediate parameter from the DMT is KD, or horizontal stress index. Basically, the formula is P0 minus U0, which is the effective horizontal stress against the membrane after penetration, divided by the vertical effective stress, which is known. So the formula is the same as K0, only that P0 minus U0 should be the effective horizontal stress. We would like to say that KD is K0, but unfortunately, it's not true because we have penetrated the soil and we have created an extra pressure. So it's not the same. It would be a miracle if it were the same. It means we would have not penetrated with the blade. But they are really, really closely related. This is probably the closest way you can go to measure in situ the horizontal stress and K0. In fact, KD is very well correlated to K0 and OCR in clay, not in sand. In sands, it can feel the differences, but cannot give you K0 and OCR. You need to do a site calibration. How do we read this parameter KD? Well, when in clay, KD is equal to 2, you are in a normally consolidated clay, meaning its OCR is equal to 1. When KD is greater than 2, you are in an over-consolidated soil or a cemented soil or an aged soil, or something that makes the performance of the soil higher and not like in a normally consolidated material. Just to give you an example, here we are in a test site where the top layer is composed of silt, sand, and clay with values of Kd close to 2. So this is almost normally consolidated, basically. In the lower part, we go in clay or silty clay, which is very, very consistent and very stiff. And as you see, Kd is much greater than 2, and this provides an indication that it is over-consolidated. And we know that in this place, these clays are over-consolidated. Now, OCR is obtained as an estimation of Kd. This was obtained by Professor Marchetti using experimental points collected in many research test sites in all the continents of the world. And he found this formula in 1980 after his studies. It's nice to show that 15 years later, these two authors, Kamei and Iwasaki, showed that the best correlation with additional points found from many other test sites was in excellent agreement with the formula proposed 15 years before by Professor Marchetti. Similar verifications and validations were done also through theoretical studies using very complex numerical modeling methods like phi, no, and u, showing a good agreement of this curve with the points and their module and their studies. I'm not an expert of CRISP or critical state modeling, but they concluded that this formula is valid for the evaluation of OCR from Kd in clay. A similar approach was used for the estimation of K0 from Kd, and this is the formula that was found in 1980 with experimental points, again validated and showing a very low scatter compared to several other possibilities and methods. Again, there is also a theoretical validation using these critical state model softwares for validating this curve from Kd. Just to show you a practical case, here we are in a landslide in Sicily some years ago. We were involved in this project. There was a landslide near the railway, a very dangerous situation. And the client wanted to do a measurement very close to the landslide and farther away to monitor the relaxation, horizontal relaxation of the horizontal stress. And from the graphs obtained through K0 for the effective horizontal stress, it's nice to see that the red profile, which was farther away, was the most healthy. And as you were getting close with the blue and the red, the horizontal stress was of course weaker. So this is also shows a good consistency for evaluating the horizontal stress. Now, the third intermediate parameter I want to show you is the dilatometer modulus ED. According to the theory of elasticity, it is defined as the elastic modulus of the horizontal load test performed by the expansion of the membrane. We are actually doing a load test from the A to the B reading, or P1 to P0. And if you accept some specific modeling of elastic semi-infinite medium that you can find in this publication, you can work out this simple solution, ED equals 34.7 times P1 minus P0. However, this modulus is not the one that is recommended to use, because again, we have penetrated the soil, so we have altered the soil. And we did evaluate a modulus, but it's not the pre-insertion modulus. So it's good that we are starting from a direct measurement of a modulus, but it requires corrections. Now, the modulus that Professor Marchetti decided to address in the correlation is the constrained modulus at the geostatic effective stress at depth. And it starts from ED with the correction of the RM factor, which is obtained using the other two information we just saw. we know the soil type, so we know if we are in clay, if we are in silt, if we are in sand. We know the stress history from the KD parameter. We know if it's a normally consolidated or over-consolidated. So when Professor Marchetti went in many research sites where they knew the modulus, he according to the soil type and KD, he found inside these three parameters the information that is necessary to estimate the modulus with the correlations. And these correlations are considered very good by the experience in these 40 years of this instrument. I reported in this slide three examples in the United States, in Europe, and in Asia, to show you the very good agreement of the modulus obtained from the DMT and from odometer data taken from high quality samples. And as you see, the agreement is very good in all three cases. And even in this case, this is the Norwegian Geotechnical Institute. They have excellent sampling methods, and the two profiles are between this shaded area show an excellent agreement with the odometer points, which maybe show even more scattered than the DMT. And this is in Japan, in between the odometer and the DMT for the modulus M. Again, a very good agreement. Just to give you an idea of how you obtain the strength parameter in clay from the DMT, you use the Schanzep relation, which is the ratio between the undrained shear strength SU and the vertical effective stress. This ratio in over-consolidated soil is equal to the same ratio in a normally consolidated soil times OCR to the power of M. This is the Schanzep relation. Now, we saw before, because I showed it in the previous slides, how to estimate OCR from KD with this formula that we can replace here. The exponent M has been estimated about 0.8 by Professor Ladd himself, and the ratio between the SU and the effective vertical stress in a normally consolidated soil generally is 0.22, 0.23. So if you combine all these expressions, you obtain a single closed formula as a function of KD and the effective vertical stress, which is known. Again, the approach of Professor Marchetti was to do the DMT tests in well-documented research test sites in order to compare the results and see if they gave the same results. Here you see comparisons with a pressure meter, with triaxial tests, with CPT in, again, very well-documented sites. And the black thick line is the DMT showing very good agreement. This is a comparison of the same parameter, CU or SU is the same, in Canada. And you see the points are the field vein tests that are in good agreement with the DMT profile. This is another comparison, again, in the third continent, in Japan, and you see that the points of the DMT pass right through the triaxial test for obtaining the shear strength. This is the research test site in Italy. Since I'm Italian, I want to show it to you. And it's the Fucino research test site. And here also they compared laboratory UU test and vein test. And you see that the black thick line of the DMT passes right through the other points, while the CPT, according to the factor that was used, and C14 or 22, the profiles vary quite significantly. This is published in the proceedings of this conference, if you are interested. Now, let me focus on the C reading 1 second, because I introduced it at the beginning and I did not explain what information or how it obtains the information. In a sense, the C reading is able to measure the pore water pressure. It is like basically a piezometer. In this example published by Schmertmann in 1988, I like to show it, but we have so many of these examples that I could show you. The water level was known at 1.8 meters. And you see this is the hydrostatic line in sands, especially the P2 values lie right on the hydrostatic line. Then in clay, the C reading is much higher. And then again, in sands, the points are on the line. So the C reading is accepted. That is the pore water pressure. If you want to understand why, we picture it this way. When the membrane expands in sands, it pushes the sand away. And when you slowly decrease the pressure, only the water comes back. And that is what closes the membrane. So that is why in sands it works. In clays, it doesn't work because you push the clay, but then of course it comes back. And so generally it's greater. This is useful because in cooperation with ID, it can confirm that you are in sand and clays. So ID independently with the C reading can give you, yes, we are in a drained layer or undrained. And it's nice to have two independent ways of measuring the same thing and when they agree. So you can use the C reading to see if you are in a draining layer or non-draining layer. Unfortunately, the C reading takes time because you have to deflate slowly the membrane back. It takes like A and B reading. So if you do also the C every 20 centimeters, it takes the double of the time of the DMT test. So normally, unless we have specific applications where we are very interested in the water pressure, we just do it every meter to have a rough idea of the drained layers and non-drained layers, in addition to the material index ID that I showed you before. The intermediate parameter UD is defined as the distance of the point to the water pressure. So when you are in sands, the point is on the line and it's equal to U0, so UD is 0. And when you're in clay, generally it's greater than 0. And so your point is above and UD is positive number. Just to give you an example of this utility, this functionality, here we are in the south of Italy in a harbor where the material was, you can see it, it was between silt and sand, so it was probably draining, but we wanted to check that it was purely draining. So we did a lot of C readings every meter, but in 5 different tests. And you see that all the time the points were on the pore water pressure and the behavior is fully drained, which is really important for the designer to know if it's a drained behavior or not. So I think the C reading is a good contribution of this instrument for the test. Now let me show you a few slides on the dissipation test. The dissipation test consists in stopping at a certain depth and performing only the A readings, basically the total horizontal stress with time. Okay, so you don't expand the membrane, never. You just test the horizontal pressure and deflate. So the membrane never moves, but measures the total horizontal stress. So you have time and A starting and remaining at the same depth. If you plot this in a semi-logarithmic time, you will see that it draws a S-shaped curve, and the flex point has been correlated to the coefficient of consolidation and to the coefficient of permeability using, of course, the consolidation coefficient in the formula. This works very well in cohesive soils like clays and silts, because you do need to take some time to take the readings from the pneumatic system. We will see with the Medusa it is much faster. This is just to show you that the dissipation performed by the DMT is in a very undisturbed area where you can inflate the membrane and involving a large volume of soil. So it really works quite well for obtaining the estimation of CH. This is the first validation. I like to show it, this historical note. In 1998, it was first published, showing a good agreement between the coefficient of consolidation from the DMT, from laboratory, and from the back analysis in this project. Now with the Medusa DMT, it is possible to monitor continuously with time, because the system that I'm about to describe can take many readings of A with time, and you have the full curve instead of just some points every 15 seconds or 20 seconds. The DMT is coded in the international standards, Eurocode, ISO standard, ASTM, and in a document that was written by the TC16 that today is called TC102, and this is probably the most appropriate document if you want more details on the DMT. Okay, still have some time. The SDMT is used in over 80 countries worldwide. This is a map of the distribution of the users who have the equipment. As you see, North America, Europe, Eastern Asia. And here there are many points missing because this is not updated. It's not so easy every time. But just to give you an idea, it has increased a lot in this southeast and in South America. So it is used basically worldwide, not so much in Africa, but it's because many European companies then go to do the test in Central Africa. They don't own equipment there. Now, what are the main differences between the CPT and the DMT equipment? This may be of interest for some of you. First of all, the flexibility in the penetration methods. I said this before when we talked about the machines. The CPT must be pushed at a fixed penetration rate of 2 centimeters per second. That's why you necessarily need a penetrometer. And the penetration rate may influence the results if you go too fast or too slow. You can imagine if you have an alternation of soft material and stiffer material, when you push it can go slower or faster. And that can change a little bit the results. The nice thing of the DMT is that the penetration is completely independent of the measurement. You push the instrument, once it's there, you start to do the readings. It's not interested in how you bring the instrument at the depth. This means you can use any type of penetration methods with a drill rig, a penetrometer on a floating barge, and so on, as we saw before, because the measurement is independent of the pressure rate. The second important point is the amount of distortions that you do. When you penetrate with the CPT, your measuring zones exhibits a lot of deformations which change the state of the soil. With the blade, you disturb, of course, because you're still entering, but much less. So the original state of the soil is, at least in good part, preserved. And especially when you do the horizontal load test, you're doing a modulus, you're measuring a direct modulus in an area that is the least possible disturbance that you can have. So it's more representative and has less uncertainty. Another difference with the CPT is that when you penetrate with the CPT, you are penetrating with a circular shape. And when you penetrate, you create an arch, the arching effect, the one that we are very happy to have this effect in tunnels. But here it's an obstacle to the horizontal stress. So the CPT measures very well in the vertical direction, but in the horizontal, it's insensitive because this very stiff pre-stressed cylinder is like a barrier to the horizontal stress. So in compaction projects also, sometimes the cone does not feel the horizontal stress because of this phenomenon. With the blade, the relation between the thickness and the width of the blade is such that when you enter, the arching is really, really limited, is poor. And so you have a good sensitivity, and also you're measuring in the horizontal direction. So this means they are good complementary tools. Also, the CPT is an excellent tool, but in the vertical direction. This is a slide that Paula Monaco, I saw, will explain further, so I will skip it. But again, it's a comparison between the DMT and the CPT. Now, the DMT and the pressure meter are the only two tools, in situ tools, that measure directly the modulus in situ. We all know the difference between stiffness and strength. So just to give you a qualitative example, here you have 3 different soils that have the same strength, but 3 different stiffnesses. So if you measure the strength, then you have to find a way to distinguish between 3 different stiffnesses with a correction factor that varies quite significantly. Another point I want to emphasize is that if you are interested in the modulus, or you have to do a deformation analysis, this curve shows where your instrument, the DMT or the pressure meter, that these 2 instruments provide a modulus in the range of the deformation analysis, because the strain at which they apply to the soil is in this order of magnitude. If you use the CPT and the SPT, you are in the high you're applying very large strains, and you obtain a modulus that is in this area, and then you have to find a way to use a factor to then obtain the modulus for the deformation analysis. This is a list of the applications that will be shown in the next presentations. Just to anticipate what will be shown, I just want to give you a few slides on the settlements, on the modulus and the settlements application of the DMT. Professor Marchetti liked very much this very simple formula, which is really, really elementary. He used to say it's better to use a simple formula and a good modulus than a long formula and a modulus that's mistaken of 3 orders of magnitude, which is quite common, unfortunately. So from the load, using Bussinesq, you can provide a profile of the stress increment due to the load. From the modulus that you can measure from the DMT, you obtain the modulus with depth, and integrating every 20 centimeters, you can obtain, of course, the settlement evaluation. From this, you obtain the primary settlement at working loads with a factor of safety of about 2.5 to 3 to bearing capacity. There are many publications showing very good agreement between the either the modulus or the settlements predicted with the DMT compared to observed settlements. Some of them are recent and published in this conference. This is a paper from Roger Valmetzger. You may find it in the proceedings. He collected over 100 projects where the project was changed thanks to the DMT, because it provided less conservative modulus for a less conservative design. And his clients send them projects where they saved money thanks to the change of the original design to shallow foundations commonly. This is also a quite recent publication from a Polish guy where you see different soil types, and basically he did a comparison of settlement values measured at the structures with respect to those obtained by dilatometer in 28 projects. These were all limited to structures with shallow foundations, and as you see, the settlement estimated from the modulus of the DMT was in good agreement with the measured one. I think this is quite precious in different soil types. Just to let's show, as we did in this workshop, if we do a DMT test, how we go to a possible settlement evaluation very rapidly, because it will be shown in detail by the next presentations. Here we are in Colombia, where in Bogota we did measurements with a drill rig during the presentations. So we had the pressure readings, P0 and P1. As you see, the readings are close to each other, P0 and P1. So are we in clay or are we in sand? Does any one of you want to answer? In clay, because the readings are close to each other. The water pressure, we did not take C readings because in clay it doesn't make sense, but they knew the water level was at 3 meters, and this is the unit weight. This is the input of the software, because it's the DMT readings. Unfortunately, we're missing the P2 because in clay, but the water level, you have to input it. It's not something that that we know. If we have C readings, we can change this value until the curve passes through the C readings, but we need sand to do this, and here it's only clay. And then the unit weight is obtained with that chart that I showed you before, ID versus ED, that gives the unit weight of the soil. Then the next graphs are the intermediate parameters, ID, KD, and ED. So ID is telling us that we are in clay. In the top, it's a little bit more silty because of this strong essiccated crust. Look, we see the crust very well in these first 6-7 meters with very high values of KD. And then KD is equal to 2. Is the one that I said. But combined with these two in the formula, you obtain the modulus M. So this is the main graph, which repeats the material index ID, but also shows the colors with the type of material: clay, silt sand, silty clay, and so on. Here it's major clay with some silty material on the top. The constrained modulus, which, as you see, reflects the fact that in the top essikated crust, which is over consolidated here, or somehow cemented or essikated, or something that makes its performance as if it were over consolidated, the modulus is higher, and then it becomes very low, because just where it becomes normally consolidated, the modulus is very low. The undrained shear strength, the KD, we already saw it, it's the intermediate parameter, and also the shear wave velocity, which has quite changes a lot compared to the material, but it's another important parameter to consider. And using the formula I showed you in this presentation, without any parameter change, you see the 1980 formula that OCR is equal to 1 up to 7, and then it goes to very high values at surface where there was that essikated crust, which I think is nice to see. It's a typical value of 1, just like K0. In the top part is very high, maybe even unrealistic. You can't have K0 so high, but it's just to show that this crust is very, very strong. The horizontal stresses are strong. But then as you go in the normally consolidated, you see it's 0.5, which is the typical value of K0 in clay, normally consolidated clay. This graph I already showed before, but also this chart can be useful to use these colors to identify the material type. Here you have the type of material with depth, and here they're plotted all in the same area. So it's just to give more information and a different viewpoint of the same information. And of course, from Vs and using the soil density that you obtain from gamma, dividing by the gravity constant, you can then obtain a G0, which of course have a similar shape to Vs, a bit more pronounced because of the square of Vs. And then this is the settlement evaluation that I'm going to skip because it will be addressed by Sara and Paola quite abundantly. Let's look at the Medusa DMT system, which is really something new. I've been working with this with Professor Marchetti since 2010. So it took really a lot of time to be completed. Now it's 2-3 years we are using it, and it's I want to share with you its potentials. It is a DMT that is fully autonomous to perform the tests. It is composed of a battery pack at surface, of an electronic board, of a motorized syringe, which is composed of 3 different pieces: an electric engine, a piston, and a cylinder for the piston to run into and to generate the oil pressure. A pressure transducer, very small. It's very difficult to find a very accurate one that was small enough to fit in a rod. And then, of course, the blade of standard dimensions, because we want to make, these are DMT measurements. They're not Medusa DMT. They're like a normal DMT. You have to get the same results. And we validated that we had the same results. Only that you use this automation with the same blade. The Medusa DMT is very compact, because even though you have this rod like the seismic that is quite long, you don't need a gas tank, which is not really simple to bring when you fly. You can't actually, you have to find it locally. You don't need the big control unit. We have a small acquisition box here. It looks very big, but it's small. And there is no pneumatic cable. You don't need to bring the gas or the fluid below, because it generates the pressure inside this instrument. It is very compact to ship and simple to transport. Now, one of the important points is that I told you before that when you do the DMT test, you have to try to take the A and B readings in about 15 seconds, according to the standards, with an error of plus or minus 5 seconds, which is not really simple for unexperienced operators, because the gas is compressible, so you can flow very fast the gas and take the readings too fast, or flow very slow and you take it slow. And this can influence the results, because when you push the blade, the water can dissipate. So it's important to have control over time when you're doing the DMT measurements. The Medusa DMT has an hydraulic automation with oil. Oil is not compressible, so, and volume controlled, so you can decide and impose the time for obtaining the A and B readings with an accuracy close to plus or minus 1 second, with an extremely high repeatability, which is independent of the operator doing the test. This, you have a complete control of the data. This is a standard test cycle. Here you have the engine current.
Diego.
Okay. You see the pressure, this is the pressure, it's increasing. The contact of the membrane is on, and this is the piston in the syringe, in the motorized syringe, and this is the engine. So the piston moves forward, the pressure increases, the contact is still on. When you get the A reading, you're measuring the total horizontal stress.
Diego.
The contact of the membrane goes off and the A reading is taken. It goes a bit faster because it needs to go faster to get the B reading in additional 15 seconds. You see here you are very close to 15 and here to 30. And so when the signal goes back on, you take the B reading and then it goes back slowly and takes the C reading when the contact returns.
Diego, sorry, can you hear me? This is Paula.
Has to do is that when you arrive at depth, he has to press a button to make this cycle start. Then he can keep his hands behind, and this will be done automatically by the automation. The first validation of the Medusa DMT was done in Poland in 2019 in this Zelazny Most
Diego,
where many standard DMT tests were done, and we wanted to also validate the system there with the company who's very open to perform measurements. It's a very big tailings dam with a dam length of 14 kilometers, and it's quite high now, above 66 meters. And we did the tests with this very good, very strong truck. And this is the Medusa DMT, and this is myself. It was quite cold at that time. And this is, in that case, we were just interested to see that it was working well, the instrument, and in particular that the top part was quite compacted and the lower part less compacted. So this was just a historical note I want to show as the date of the first validation of the instrument about 2 years ago. And now, just to give you a more modern view, this is a test we did in Rome, in the near Fiumicino, which is the airport of Rome. This is a new pavilion, well, it's relatively new, of the pavilion of the new exhibition center of Rome. We did the test inside with our truck and also outside. It would be interesting to go in the geotechnical aspects of this problem. Basically, they put piles only at the corners, and they had settlements all on the rest. So here it's up, and it settled in all other directions with really a lot of problems. But I cannot talk about this even because it's not my project. But I just want to show you because it was a good experience for me. Here, we did the test up to 60 meters. The soil is really, really soft. Here you see.
Diego, can you hear me?
1 and 2.
We don't see the video from home.
Mostly clay, but sometimes sand, because the readings are farther away. We will see that also in ID, but you see it already from the C readings, which we did, I think, every 20 centimeters, because with the Medusa, it's easy to do also the C reading. You still take time, but he does it automatically. And you see every time the point lies on this line, it's a sand, whereas when it's far from the line, you're in clay. This is the unit weight estimated from the DMT. And this is the general main graph, as I showed you before. So you have mostly clay and some layers of sand that we saw before also with the C reading. The modulus, you see very, very soft material between 5 and 12. And terrain shear strength, friction angle, and basically it's a normally consolidated clay. We also did a dissipation test. We left the Medusa to do the dissipation test a whole night. So it took all the points up to 10,000 minutes. And this is the flex point and the coefficient of consolidation and permeability. We did an additional effort. Excuse me, Alessandra, can you please move because the camera is...
Yeah, no, it's powered. Just from the video disappeared for people connected on Zoom.
Oh. Shall I wait?
I think you can go on.
Okay. So this is just to show you that in 2021 we completed, but 2020 we worked to add also the seismic sensors to the Medusa, so that it was a Medusa SDMT and not only DMT. This was done by adding the seismic board and some details that are shown in this graph. I don't want to discuss, but thanks to the EIT raw material support from the European Union, we were able to do this addition. And now, just to give you an idea, tests were performed in May, again with the truck, in this paper factory in the north of Italy. And besides the DMT readings that you see here, we did also the seismic. Here, very clear, you see the... Oh, this is gone. So here you see the clay material, and then well, clay or sand anyway. But here it's very clear that you are in sand because the second reading is much greater than the first. Here, for scale reasons, you don't see it, but it's the same. And again, here below, clay and sand. Unit weight. This is the main graph. Again, up to 30 meters with the colors for the type of soils, the modulus of the sand, and this is the critical layers with very, very low modulus for the project. And of course, thanks to the shear wave velocity, we have also the profile of the shear wave. Now I want to introduce, this completes the introduction to the DMT, SDMT equipment. Medusa, I want to say a few words on the partially drained geomaterials, some of which will be repeated and amplified in the workshop of this afternoon. Just to tell you of certain soils that are difficult for the DMT. I said that the A and B readings should be taken in 15 seconds. So when you are in sand, A and B are both fully drained because the water dissipates very rapidly, and it is very simple, and the correlations work extremely well. In clay, A and B are fully undrained because by the time you take the A and B reading and you do the expansion of the membrane, they are fully undrained. In most silts, A and B are partially drained in the sense that during the test, the water dissipates. But in several of them, the interpretation is still okay for the silts. However, Professor Marchetti in 2015, after several experiences, including the one in Austria, in Salzburg, but many others also, there is a small family of silts where A and B are partially drained to a different extent. So B minus A is too low, is not real. And the intermediate parameters, ID and ED, which are function of B minus A, are too low. And the modulus M, which is function of ID and ED, is underestimated. Just to show it graphically to you, if you do a dissipation in clay, you see the readings, which are at about 15 seconds, are both undrained. When you are in sand, you have a very rapid drainage, and both readings, A and B, in 15 seconds are considered perfectly drained. The problem is in the niche silts that the A reading is partially drained or almost undrained, and the B reading, by the time you go to 30 seconds, which is additional 15 from after A, you have a very low value. So then all the parameters that derived by B minus A are underestimated. Of course, this is a problem with also other tools with the CPT. It's basically almost impossible to solve, but we are working at it. Now, first of all, detection. We want to identify when we have this problem, because this way we know that the results have to be looked at with care. So the DMT is able to detect the partial drainage because we have those 15 seconds at the beginning in which we can monitor the horizontal stress of the A reading with time. So a possibility can be that if we have no appreciable drainage, then we are either in sand or in silt, and we just continue normally and to the B reading in 15 seconds. If instead, during the 15 seconds in which we are trying to take A, when the medusa, because only the medusa can do this, is in equilibrium with the horizontal stress, sees that there is a lot of drainage, like 20% or 15%, then you wait and continue the dissipation for 1 or 2 minutes, and when the value is stable, then you expand to B. So this is what was proposed by Professor Schneid in his first paper in 2019, and now also in the Mitchell lecture to this conference, he said a few additional words, and we are working on results we took together in Brazil in a test site of silts. This is to show you what I just said. You have 15 seconds to take A. Instead of taking A only at 15 seconds, you do like a dissipation. You continue to take the A reading with time, and you have a very small decrease of A. So in this case, you say, no, I just continue to B normally and then C. So this is like a standard DMT. I will take the last value of A at 15 and then the B and the C as if I did it normally. However, in this example, here we are in Araquari. Sorry, I didn't write it, but we're in Brazil. In this case, the value here, I will show you in the next page, is a significant decrease of A with time. So we waited 100 seconds, and only later we expanded to B and then to C. You see this contact goes on and off because we are taking a lot of A readings. The motorized syringe is going crazy really fast to stay in equilibrium on the contact A to monitor the horizontal stress. And then after 100 seconds, we said, okay, now go. And he expanded the membrane to B and then back to C. This is the same data before, just to show you a better scale of this dissipation test only without the B and the C. You see from about 450 down to 320. So a very big decrease. And if you plot it in the log scale, semi-log scale, you can obtain the flex point in between 10 and 15 seconds. Actually, between 10 and 20, this is probably 15 seconds, which is when you take the A rating. And that's why if you use the standard interpretation with the standard method, you will have difficulty to get a good modulus and good parameters. In parallel, Professor Monaco et al. Wrote a paper that will be shown in this conference, I think on Tuesday, and they showed that a slower than standard penetration rate, in addition to the pressurization rate that I just showed, can change the behavior towards the drained behavior, while a faster than standard penetration or also increasing the pressurization rate shifts the interpretation towards undrained behavior. So we have these two variables of the penetration rate and of the expansion rate, which we can do faster than normal to try to account for this partial drainage. The last procedure I want to show you with the medusa, which is not possible with the standard DMT, is the DMT while penetrating procedure. We said the system is able with the motorized syringe to maintain the membrane in equilibrium in the horizontal direction. So why not do like the CPT? You continue to penetrate and measure the horizontal stress. So you're very fast, like the CPT, and you get the A at time 0, basically, during penetration. So perfectly undrained. And that's something that we are exploring. And you plot the A readings with depth. Perhaps you can take the B reading when you have to change the rod that you necessarily have to stop with most penetrometers after 1 meter. And so you can obtain also the standard DMT measurements. The first time this procedure was done was in Brazil, in Rio de Janeiro. There's a paper that I will present at the conference in the next days. And this is the standard A reading in clay. And we thought of this procedure only the last day that we were doing the last test, the second Medusa DMT test. And fortunately, we were able to capture the difference of soil. Here we expect the same behavior because we are in clay. So the standard A reading with a standard procedure should be similar to the A reading with the Medusa in continuous penetration. Of course, this is just the beginning of something that we want to explore. This is an additional test we did with Professor Monaco that we are sending at Sydney at next year's conference. Sorry, this is 22 because it was delayed to next year. And this is a full test of the A reading while penetrating, and the points are the B readings. So P1 are the points every meter when we change the rods. And the C reading show that in clay, we are in clay, of course, because they're much larger than the water pressure. So this is what I wanted to present. If you have questions, you can pose them now. How much time do we have? 10 minutes. You can pose some questions now. If you look for documentation, you can go on the website. On LinkedIn, there are several of these projects. We like to show them so that if you're interested, you can look at them. So you can decide to look at this, subscribe to this LinkedIn post that we make. Okay, thank you for your attention, and I am ready for questions both from here and from the web.
In the SDMT, is there any possibility of realization of the geoforms or not?
Good question. Yes, I did not go in detail in this. The SDMT sensors are deliberately monoaxial because we want to measure the vibrations only in the direction in which we generate them. So in the training that I did not show here because it would take too much time, we say to put the hammer in a certain direction so that when we hit, we vibrate in a plane, okay, and in one axis. And so when we put our rods, we orientate so that the sensor is sensitive only to that axis. Most systems put triaxial or 5-axis sensors, and you receive a lot of waves also bouncing in different planes. And then, of course, it's very good, but then you have to use a lot of processing, filtering of the signal to choose and select only your waves. The principle with this instrument is to make it very simple. You are in one plane, you make the vibration of the soil in one direction, and you listen only in that direction. And that's why you get very clean waves.
I was meaning the orientation in the horizontal plane, just to be sure you are horizontal with the impact.
Yes, well, when you put the blade, you have to put it in the right way and it will not turn, okay? When you combine it with the CPT could actually turn. But let me tell you that the sensor is fixed with in a certain mechanical way that even if it's not perfectly parallel, but a little bit tilted, there is a small component that will go. Of course, if it's perfectly 90 degrees, it will not sense. But even like this, it will simply be weaker, the signal. But if you do the cosine or sine, I don't know, you get the, and so it has not been a big problem. It's good to start in the right axis perfectly, and then if you have a small error, it will work. No questions. Probably they fell asleep, all of them, online. Any curiosity, even comments or experiences?
I have a short question regarding those soil behavior factors like ID or EP. Those classifications, have they been originally developed based on the ASTM standard or ISO standard or the Euro code? So what was like the the original idea to define a clay or a silt or a sand, because when using different standards, those transitions between clays and silt, they will move. And so I was wondering, because a lot of those niche silts, they are always situated in the clay area. Those niche silts, based on the Eurocode, they are classified as silts. But when looking at those soils and characterize them based on the ASTM standard, they are classified as a clay. So looking at the ASTM standard, the classification of the dilatometer would be perfectly right. Looking at the Eurocode, the classification will be okay, but not perfect. Fine.
Look, in the niche silts, everything is completely out of the scheme, because you are starting from measurements that are not like the others for that drawing I showed you of the drainage. So in my opinion, you can try to do the corrections like we have seen already from Schneid and try to use the standard interpretation. But I think that after these studies, we have to see if it will be possible or if we have to create a different classification, because that system was done to make a rough estimation between clay, silts, and sand, and it works very nice. There's so many publications showing that clays and sands and silts work well, and now with the C readings that we're doing very commonly, we always see an excellent match between clay, silts, and sands. But indeed, the niche silts are horrible, unfortunately, and I know also with CPT, we are working with many companies we do both DMT and CPT at variable penetration rates, like Paula will show in her presentation, and to try to link some other parameter for that. So if your question is the niche silts in that chart, I think we have to work on that, because it's a very specific type of soil that was not included originally there, because it goes in the weak point of the DMT and in the CPT, where you cannot control. If you do a small change, it will change a lot. It's too sensitive to the variations. But for clay, silt, and sand in general, it works very well. This is what I think.
How about the reliability of the test precision when it comes to soft tracks, for instance, sandstone?
To soft?
Soft tracks, like mudstone or sandstone. Those are, I mean, this method can provide some results that we can use.
When you are in a soil, you always have to think of the mechanics of the DMT. So to answer your question, I think it's this way, that when you are in a material where with the penetration of the blade, you open it, like for example, in a rock, you crack it, even if you could measure it and you could penetrate it, it would not be valid in terms of interpretation. In like crushable soils or materials, I don't know if you're, because yeah,
that transition zone, because you can still penetrate, but it's not, and that material is not as strong as rock, but it is still like in the transition. Again, it's like it falls into that transition zone that you stated earlier with silt. So like it's not easy to differentiate, as you know, but still we need some parameters like undrained shear strength, for instance, like in UK.
Okay.
But that was my question of interest. Like, have you ever had an experience with this test?
Not directly, but the first thing I would do is a dissipation test to see what happens to the aridity, because that's, as I showed you, it's really important to detect and to understand if there's something going on during the measurement. The second aspect is the penetration. Of course, if you penetrate and you completely break the bonds, then you will measure something different. But at that point, I didn't have the time. I wanted to add this, but there was no time. It's really important to have VS, because the shear wave velocity does not depend on this, is not affected by this problem, because the wave travels in the soil that is not disturbed. So what we are doing, but again, I would like to have time to explain it maybe in another place. There are some publications on this, is to the ratio between Vs and the modulus M. Because if Vs is very high, maybe you are in a cemented soil or something that originally before penetration is with higher performance. And then once you penetrate with the blade, you disturb it and you measure something that's much weaker. So if you do a ratio between that, actually it's a ratio between the measured Vs and the estimated Vs from DMT. We have a large database and we found the best correlation between the DMT parameters, ID, KD, and ED to Vs. And that's for average soils. And when you see, oh, but it's not average, Vs is much higher than the standard DMT, then it means you have cementation. And that when you penetrate, the blade weakens the soil and you have lower parameters. Instead, the Vs is really fast because it's in the original soil. And that is an alarm to have to detect. And then you say, okay, now how do I react? In that case, I know that many take G naught from Vs and divide by a constant. But now we're trying to do something better with these variations of measurements. Perhaps not take 15 seconds to do A, but maybe 5 seconds, or 0 seconds for A and 5 seconds for B. Go as fast as you can to B in expanding, so it's undrained. And that's what we're working on, but it's not mature enough to be used. And we are working also with Simon.
They're trying to make some progress with this.
Yes, with Professor Schneid from Brazil, he says to work a lot on this with the DMT, because since we can change the procedure and the speed according to where we are, I mean, with the CPT, you have to change the penetration rate, and that you have to decide before, and you don't know what's happening. Instead, with the DMT, you can push, you can detect if the reading is going, if the A is dissipated, and you can decide, no, I will do a standard reading, or no, I will wait for the dissipation. So that's something that gives you more chances, and you can put it in an algorithm of the Medusa, and he will do it according to what's going on. So that's where we are trying to go.
Generate the S-waves with the inverse direction of the effect, or never?
We don't, because with this system, the idea is to generate a wave arriving to one sensor, and that same wave has to do just half a meter more. And we don't want to give one impact on one side and one on the other, for the reasons of what I said. I don't know if you heard it when I talked about having only one sensor. You have to give 2 hammer blows. It's impossible to give them the same. Even when you revert, it will be different. And so I know you want to have the 2 polarizations and then poke the point, but you lose a lot of accuracy. It's better to have only one wave, and to see the same wave, how much delay. Think about when you go with the car, you want to run, and you have the speed cameras. They take here and do the average speed. It's only one car going. If you have 2 different cars, or I like to also say, if I have to measure this length, do I put my ruler here, or do I do from here to here, from here to here, and then make the difference? I have a log error. So differential is always better. One sensor here, and then you say, I don't care what happened in the past. I want, or before, I just want for the delta. And there you gain a lot of accuracy in differential measurement.
There is no trigger for the wave.
Electrical trigger. Yes, in the second DMT conference in Washington, Professor Main, that maybe you heard of, he manufactured these automatic hammers with a spring loaded, an engine that would then hit. But it was a small mass. It worked well for the first 20-25 meters, but if you want to go deeper, we have seen it's not so simple. Many users have asked to design one and to make it, because you want to press a button and it hits, not have a person that always have to hit. But it's not so simple. It's big and heavy. So we recommend what I showed you, perhaps making the pendulum system so that you can just pull a rope. It would be difficult to ship and too expensive. I don't know. For the moment, we cannot do it. We would know how to help someone construct it, but it looks like the market, no one wants to build it. It's expensive and difficult to market. So we try to give the indications with that hammer, and then usually the users find a way to automate it with some, maybe they pull a rope from the truck and then they leave it, and it's. No questions from the internet. Are you sure it went the Zoom? Okay, well, I think you really deserve the break now. It's 11:04. Thank you for your patience, and try to be here by 11:30, 11:35, so Paula can start on time.
Okay, so can I start, Diego?
Yes, please start, Paolo. It's
Okay.
I don't know online if they see it, but I have no way to check.
Okay.
They tell me that it's okay.
Okay, just let me know if there is any problem because I don't see the chat with the screen now. Okay. So good morning, ladies and gentlemen. I will present the second part of this course today. Will be as Diego anticipated, will be about the DMT and SDMT design applications. I am Paola Mo, University of Aquila, Italy. I'm sorry for not being with you in person today, but I'm happy to join you online. And I am a little bit disappointed because so far I haven't missed one of these conferences on the site characterization, as also did Silvano Marchetti. Now had the privilege to cooperate with Professor Silvano Marchetti for about 30 years at the University of L'Aquila. So as Diego said before, we will not be here today talking about the DMT without him. So before entering in the details of DMT applications, I have to focus on some that are the major distinctive contributions that the DMT offers in routine site investigations, because these have a relevant influence also on the applications, as we will see. The first one is the information on stress history incorporated in the parameter KD, the horizontal stress index, and stress history has a dominant influence on soil behavior. And the second one is that being an in situ pressure displacement test, DMT results are closely related to a working strain soil stiffness than penetration tests, and this is reflected by the constrained modulus MDMT primarily. Also, the seismic DMT, in addition to the usual DMT results, provides also the shear wave velocity and therefore also information on the small strain stiffness. Research over the years has found the centrality of the horizontal stress index KD, which is a key parameter obtained from DMT interpretation, and one of the few in situ parameters able to provide information on stress history, especially in sand. We must recall that this reflects cumulatively various stress history effects, which include over-consolidation, in situ stress state, but also aging and other effects. And as we will stress later, knowledge of stress history is fundamental for realistic predictions, for example, of settlements or liquefaction. An important observation is that many researchers have found that KD from DMT is much more sensitive to stress history than the cone penetration resistance, either in monitoring compaction in the field or in calibration chamber tests. So just to enter in some detail, this figure that Diego just mentioned before shows the results obtained in calibration chamber tests in Busan Sand from a group of Korean researchers. And they perform a different CPT and DMT tests in this calibration chamber, in which the samples were over-consolidated to different values of the OCR 1, 2, 4, and 8. And the results shown in this figure compared the normalized cone penetration resistance as a function of the relative density on the left and the horizontal stress index KD from DMT as a function of the relative density on the right. It can be seen clearly that KD is much more sensitive to stress history, to the consolidation rule, than the normalized penetration resistance on the left, because in this case, the data points of a normally consolidated and over-consolidated specimens are almost lined on the same line, while here a trend reflecting a different over-consolidation can be really observed. So therefore, we can observe that the cone penetration resistance reflects essentially the relative density, only to minor extent the over-consolidation, while KD reflects both, in particular the stress history effects. So this is an important premise to our further discussion. This is a list of the main DMT and SDMT applications that I will talk about in the next minutes. So let's start with the first one. The first application is prediction of settlements of a shallow foundation. And this topic has been introduced by Diego before, and we can also consider that probably the prediction of settlements is a #1 DMT design application. The settlement usually is evaluated by a very simple one-dimensional approach, and by introducing the constrained modulus MDMT in this formulation. And this settlement evaluated in this way is assumed as the primary settlement of shallow foundations under working loads. As already mentioned by Diego, there are many papers and histories which document a good agreement between the measured and DMT predicted settlements and moduli. We will just, this is just an incomplete list. I would like to show just some of these main case histories. This is a very famous case reported by Dr. Schmertmann in 1988, referring to the design of the Sunshine Skyway Bridge in Florida. In this case, a huge amount of CPTU and DMT and site investigations were carried out. It was found that the constrained modulus estimated from DMT was around 200 megapascal, while the corresponding value obtained from laboratory was only of 50 megapascal. And the modulus back-figured from the observed settlement was around 240 megapascal. So in this case, the prediction of settlements obtained by DMT was much more closer than to the reality than the laboratory estimated values. Another case was presented by Paul Main some years ago. In this case, the settlements were measured and predicted under a dormitory building in Atlanta. And it was found that the prediction obtained from DMT was nearly coincident with the observed settlement, while the prediction obtained from SPT values was much lower, involving a large error. Also, this error was not on the safe side. Is the case of the Tresporti test site in Italy, near Venice, where a full-scale trial embankment of 40 meters of diameter and almost 7 meters high was constructed and monitored through its life from the start of construction, after end of construction, and after removal. In this case, some of the instruments installed beneath the embankment were the sliding micrometers, which were able to provide very accurate measurements of the local vertical strain every 1 meter of depth below the embankment. And the interpretation of these settlements permitted to back calculate value of the constraint modulus, which was compared with MDMT in this figure, and it was found a very good agreement between the two moduli, especially in the soil layer between 8 to 20, which was responsible of the greater part of the settlement in this case. This figure is from a paper that we presented in DMT in the DMT conference in 2006 in Washington, and is a summary of the experience available at that time on case histories, including comparison of DMT predicted and measured values. And this figure shows a good agreement for a wide range of soil types, for settlements and also footing sites, with an average ratio between DMT calculated and observed settlement of about 1.3, with a reduced scatter between the observed values compared to the predictions. Another example presented by Berisayevich regarding the case of the foundations of a silo, which in Belgrade, in which the settlements were very, very high due to the presence of a very soft soil layer. In this case, the measured settlement was about 63 centimeters, while the DMT predicted 77 centimeters, so with a slight over prediction, but in general agreement. This figure was already shown by the recent comparison of different cases of measured settlements and predicted by DMT in different soil types. So in this case, similarly to the previous events, the agreement is generally found very, very good. And so all these previous considerations let us conclude then that the constrained modulus M obtained from the DMT interpretation can be assumed as a reasonable working strain modulus, which is able to provide realistic prediction of settlements of foundation scale load. So there is the next step that is offered by the introduction of the seismic version of the DMT is to benefit from the fact that the SDMT provides routinely at each test depth information on stiffness at two different strain levels. One is the small strain shear modulus G0 that can be derived from the measured shear wave velocity, and the other one is a working strain modulus that is represented by MTMT that can be converted in an equivalent shear modulus. And these moduli refer to a working strain level. Therefore, a tentative approach was devised to derive in situ decay curves of the normalized shear modulus as a function of from SDMT. The proposed procedure was to adapt to fit reference typical shape curves through 2 points which are represented exactly by the ratio G over G naught at small strain and GDMT over G naught at a given working strain. The problem was which is the strain range which can be associated to this DMT modulus MDMT or GDMT. Preliminary indications provided by Mena and Ishiara a long time ago located this moduli in a range that varies from 0.01 to 1%. But this, of course, was just an approximation. So the next step was to try to locate more exactly this strain range. And therefore, in this paper of some years ago, it was tried to compare SDMT data with reference stiffness decay curves obtained in different soil types by different methods, that is backfigured from observed behavior under full-scale test loading, such as in the case of the reported trial embankment, also obtained by cyclic dynamic laboratory tests or constructed by combining different in situ laboratory techniques. The procedure is explained in this figure by consisting in obtaining G naught from the measured BS and GDMT corresponding to MDMT from current DMT interpretation by using the elasticity theory, of course, as a first approximation, and then evaluating the ratio GDMT over G naught, position this ratio on same depth reference stiffness decay curve provided by one of these methods, and then by intersection locate the strain, the value of the strain, the shear strain corresponding to this ratio. By this procedure, it was possible to find different ranges of the shear strain, varying depending on the soil type. So, general lower values of the shear strain associated to sand, a little bit higher values associated to clay. It was also based on this, the interpretation of this data, a formulation, an hyperbolic formulation was proposed for the equation of this G over G naught versus gamma decay curve. And the figure below shows a comparison between the curve estimated from this equation for a clay site near L'Aquila, and the corresponding curve obtained in laboratory from resonant count test. So this approach has a potential, of course, there is still research ongoing on this topic, but there's a lot of potential applications that will be addressed also by Sara Moroso this afternoon. For example, for deriving the soil input data for seismic ground response analysis, but also in static conditions for numerical modeling, for example, of deep excavations. So another important application is of the DMT and SDMT is monitoring ground improvement. This topic has received increasing attention in the test aids. In monitoring compaction jobs to quantify the gain of soil improvement, which is of course the target of this using these techniques. Here is just a summary of frequent ground improvement techniques, which may be also largely different between them, but I will not go into details about this. The thing that many researchers observed over the years is that usually the DMT has been found about twice more sensitive than the CPT to detect the benefits of soil improvement when obtained after the treatment and before the treatment. In particular, Schmertmann, Yendeby, and others also observed that the increase in the constrained modulus MDMT was about, after the treatment, was about twice the corresponding increase in the cone penetration resistance, and also that the DMT was more accurate in detecting improvement in layers in which these benefits were not detected, for example, by CPT. And these figures show the ratio of the modulus MDMT, the constrained modulus from DMT, over the cone penetration resistance obtained before and after a compaction treatment in two different cases and two different sites. The case on the left was reported by Yendeby in 92. The case on the right was reported by Balakowski and Kurek in the DMT conference in Rome in 2015. So the sites are different, but the trend is similar. So we can observe that the white dots refer to pre-compaction, the black dots refer to post-compaction, and there is a notable increase of this ratio after compaction. And it is possible to identify also some ranges of the values of this ratio, let's say over 10, 12, that can discriminate between the pre-compaction and post-compaction conditions. And considering that compaction is a sort of imposed over-consolidation stress history, this finding pointed out the potential use of this ratio MDMT over QC as a broad indicator of over-consolidation in sand. Other experience reported by Professor Van Impe's group referred to vibrocompaction technique application on a loose sandfield in Belgium. In this case, we can also see this figure, the comparison between the profiles of KD and MDMT before and after compaction. And in this case, the benefit of compaction is clearly highlighted by both parameters, but more evidently by the constrained modulus, showing an increase of even up to 10 times. A different technique, ground improvement technique, is in the case reported by Roger Feilmetzger, resin injection, in which also the comparison between both KD and M from DMT pre-post compaction, pre-post treatment were able to clearly detect the benefit of the ground improvement. Another case history was presented. Dr. Sharif, I think he's here today, so he probably could explain this much better, much more in detail for the interested persons. But just to go to the results, also in this case, there is here is a plot of the modulus M from DMT and the cone penetration resistance, and also a plot of the ratio of M over the cone penetration resistance that clearly indicates a range of these values after the treatment that is similar to the previous reported values. Recently, some experience with the use of SDMT to detect ground improvement was gained in the area of Christchurch in New Zealand after the earthquake sequence of 2010-2011, where a large trial experiment on ground improvement was launched. This is just an example because in this case several techniques were applied and compared. at one of these sites. In this case, treatment, the ground improvement treatment included the rammed aggregate piers with different spacing. In this case, we can see that the profiles of parameters obtained from DMT and also the compenetration resistance from CPTU were compared, comparing the results obtained in the natural soils, the black line, and the red line is the intertreated soils, and it is evident that the benefit of the ground improvement are clearly evidenced by the constrained modulus, by KD, and in this case also by the compenetration resistance. More recently, an experience with the same ground improvement type, the rammed aggregate piers, was carried out at an experimental site in North Italy, Bondeno, in which a blast test experiment was carried out in 2018. And paper has been accepted, is under publication, but this is just an example of the results in which the comparison is between the parameters obtained in the natural soil, the black lines, and in the treated soil, the green line. And in this case, we can see that very clearly by inspecting the KD and M from DMT from seismoscintillometer parameters, there is an increase in these parameters after the treatment. Okay, now we talk about the different topics, which is the use of DMT for detecting slip surfaces in over-consolidated clay slopes. And a method has been devised for identifying if an over-consolidated clay slope contains active or even old quiescent slip surfaces that could reactivate, for example, after an excavation, by inspecting the profile of the KD value. The principle illustrated in this line is that the landslide, the sequence of sliding, remoting, and reconsolidation produces a zone of sheared zone of clay, which goes back to a nearly normal consolidated state. Then, if we inspect the KD profile, and we found that in this profile, we found some layers where KD is nearly equal to, and therefore lower than the values of KD typically found in which are substantially higher, then these layers are highly likely to be part of a slip surface. So the method was codified, was proposed in these terms, use KD equal to as an identifier of zone of normally consolidated clay in a slope which otherwise exhibits an over-consolidated profile, where typically KD is much higher. Looking for a specific value, KD equal to, not simply for weak zones. And in this application of this method, we can detect even quiescent slip surfaces which could reactivate. This information is not provided by inclinometer measurements because the slope must be moving at present. But on the other hand, of course, we cannot establish if the slope is moving and how fast. This is an information that we can obtain from inclinometer or other measurements. But in many cases, DMT and inclinometers can be helpfully used in combination, for example, by using the KD profiles to optimize the location and depth of inclinometers. This method has been validated by comparison in different over-consolidated clay slopes in which the position of the slip surface was known and documented from inclinometer measurements or from other information. And these are two cases in central Italy, in which in both cases the KD equal 2 values were found in correspondence of the position of the documented slip surface. And this is another well-known landslide in central Italy, in Todi Hill, which this land was investigated and monitored over the years, because it's a very complex multiple regression sliding. This is just a qualitative reconstruction. And a series of DMT tests carried out at different locations along a longitudinal slope of this longitudinal section of the slope permitted to locate the different depths at which the values of K equal to much lower than the corresponding values at other depths. And the comparison with the inclinometer measurements nearby generally confirmed that these were the position of the multiple in this slip surfaces. An interesting case history was investigated some years ago in the Chieti Hill in central Italy, in which the problem was that a new public building, a very massive public building, had to be constructed on an over-consolidated clay slope, which exhibited in other part of the slope some stability problems. So the owner were concerned about the stability of this portion of the slope. And for this assessment, a series of DMT tests were carried out just across the position of the new building to be constructed. And it was found that right in this position, the central part of the slope was infected by several layers having KD equal to, which were indicated the presence of past or present shear planes, different from the price of KD obtained on the right, on the left, so outside this zone, in which the clay was essentially sound, with much higher KD values. So this information was very useful because it was taken into account in design. It permitted by the original project to increase safety of the buildings, for example, by evaluating the stability of this portion of the slope by using the residual shear strength parameters, reducing the weight of the building to increase the factor of safety, and also to extend the foundation piles clay below this zone. It can be noted also in this figure that besides the profiles of KD, which are the black ones, the gray ones represent the profiles of the cone penetration resistance obtained from nearby CPTs. And it can be noted that if we compare the profiles of these values inside the weak zones and outside the weak zone, there is a much larger variation in KD compared to the corresponding variation in the cone penetration resistance. This case was also mentioned by Serge Leroy in his ranking lectures, or ranking lecture of 20 years ago, as a significant experience on the use of an in situ test for detecting slip surfaces in this kind of materials. And so a more recent paper was presented in PIFE at the latest ISC conference in Gold Coast. And he performed the DMT test before and after landslides, and he found that the KD values before the landslide were about greater than 4 generally, and after the landslide, these values dropped down to values nearly equal to in correspondence of the sliding surface. Okay, this case has already been shown by Diego, so I will go further. And let's change now the application is where we'll talk about the design of laterally loaded piles. And actually, I have to say that the original stimulus that induced Silvano Marchetti to develop the DMT many years ago was to implement a tool for obtaining parameters for design of laterally loaded piles. These sketches on the left are just different configurations that were proposed at the beginning of this adventure, and before arriving to the final DMT as it was proposed finally. Actually, there is a similarity. There are some similarities between DMT and laterally loaded piles in that both are structural elements installed into the soil, and both are to lateral deformation. Two methods are recommended for estimating the PY curves from DMT data. The first one was proposed by Robertson and applies to clays and sand. And this is substantially an adaptation of earlier methods in which, let's say, laboratory soil properties are inferred from DMT data. The second method was proposed. It applies only for clays, and is a more straightforward procedure for deriving the PY curves directly from DMT without the correlation chain for obtaining the laboratory soil properties by DMT. Both methods apply to the case of single pile and first-time monotonic loading. And this is a detail of formulation of the PY curve in the Marchetti method, which is a hyperbolic tangent formulation. It can be noted, an important thing is that the initial slope of this curve is derived from the dilatometer modulus, so it is related to stiffness, while the ultimate lateral soil resistance is related to the minus U0, so it is related to the undrained shear strength of clay, basically. These methods have been validated based on the results of lateral loading test on full-scale piles, different size. This is an example of a normally consolidated clay in Italy, in which both methods, Robertson and by Marchetti, produced similar predictions, which were found in very good agreement with observed displacements. Other of the DMT is about the design of diaphragm walls, but in particular we will concentrate on the derivation of input parameters for finite elements analysis in the case of deep retaining walls of deep excavation. This is an important application, and many times a very popular tool that used to analyze this kind of problem is Plaxis software, which has incorporated the hardening soil constitutive model, which was proposed by Vermeer, and started producing the Porto ISC conference many years ago for describing how to derive the different stiffness values which are required by the hardening soil model, which has basically these three values: the Edometer modulus, the E50 modulus triaxial, and the unloading reloading modulus, all referring to a reference. Well, it was found, it is explained in this paper, that all these three modulus can be derived using from MDMT, which is the basic reference stiffness. And this is a very useful information. And more recently, considering that another an upgrade hardening soil model, which is incorporated in Plaxis, is the hardening soil with small strain, which takes into account also the non-linear behavior of stiffness with strain level. We talked about this topic before. So now there is the possibility of using fully the capability of the seismic dilatometer to obtain information on stiffness at two different strain levels. There is an interesting case on the application of this SDMT for estimating stiffness parameters to use with the hardening soil small constitutive model. The case refers to an excavation of a metro station in Barcelona, was presented by this paper by Di Mariano and colleagues, and also a paper is will present some details in this conference in Budapest. So in this case, it was possible to infer all the parameters required by the hardening soil small model, including also information on the small strain stiffness and on the decay of the normalized shear modulus with the shear strain by using this conventional fitting proposed by the method, the model, the hardening soil small model. Noting that all these parameters, both constrained modulus at working strain, let's say, and also the full shape of the decay curves of G over G naught versus gamma were inferred from SDMT using the methods described before. So then the comparison between the results and the high quality monitoring data in general indicated good agreement for most phases of the construction process, which was very, very complex, very articulated, supporting the use of SDMT in numerical analysis of deep excavations. So the final topic, the final application that I will present concern liquefaction assessment, which is a topic that has attracted large interest by researchers in the last years. So I will try to give an overview of recent experience and trends on the use of DMT and SDMT for liquefaction assessment, to introduce the basis of the correlation for estimating liquefaction resistance from the horizontal stress index KD, which is a sensitive indicator of stress history, as we already stressed many times before. We will see some recent correlations for estimating the liquefaction resistance from KD, and also from the combined use of DMT and CPT, which is a further improvement of this relation. And finally, there is some observation on the estimated liquefaction resistance from shear wave velocity and from KD, which is possible using the seismic dilatometer. So the framework in which these approaches were developed is the well-known framework of the simplified procedure introduced by Sid and Idris, in which liquefaction is assumed to occur if the cyclic stress ratio, which represents the seismic stress or the seismic demand on a soil layer, is greater than the cyclic resistance ratio, which represents the liquefaction resistance of the soil at any given depth. Usually, the cyclic resistance ratio is evaluated by well-established methods based on in situ test results, starting from CPT, SPT, and also shear wave velocity, which can rely on vast experience from documented case histories on liquefaction in real earthquakes. Given the semi-empirical nature of these simplified methods, there is a general recommendation to evaluate the cyclic resistance ratio by more than one method. So here is a list of recommendations by many authoritative authors. So, in principle, it would be better to develop more procedure to improve the number of existing procedure. In this field, of course, the research is ongoing continuously. And on the other hand, as we consider the possibility of estimating the cyclic resistance ratio from laboratory or from calibration chamber testing, the major obstacle, of course, is obtaining undisturbed samples unless non-routine sampling techniques are used, such as ground freezing or a gel pusher sampler or so. So usually laboratory experiments are carried out on reconstituted sand specimen, but the adequacy of using such reconstituted specimen, even exactly at the same in situ density, is questionable because some main features of the soil, such as fabric, cementation, and aging, are completely obliterated by the reconstitution process. And these factors can affect significantly the liquefaction resistance. So several investigators have noted that the cyclic resistance ratio increases markedly with age. Aging in sands is generally attributed both to chemical and mechanical factors. It is necessary to account for stress history and aging for reliable estimates of liquefiability. And this accounting to account for age of soil deposits, some authors have proposed to introduce correction factors that depend on the age of the deposit. However, this factor is specific because the gain in liquefaction resistance due to aging can depend on many ambient factors. So in principle, it would be preferable to use a testing tool more sensitive to aging. The importance of aging, stress history, and aging action behavior has been outlined and highlighted by many researchers, starting from Mike Jabiorkowski. So the general recommendation is to take into account this factor because the predictions of liquefiability of sand deposits without taking into account these factors may be generally over conservative in many cases, or in any case not accurate. So there is a long list of reference which point out the importance of overconsolidation and aging on liquefaction resistance, and also stressing that current correlations for estimating liquefaction are heavily weighted by data from hydraulic fields of very recent deposits, which is not the generality of the soil deposits. And also, in general, regarding aging is equivalent to omitting a primary parameter in a correlation, leading possibly to an overestimation of the liquefiability, and also a big dispersion of the prediction. So this is just to make a general recall of the available experience, which points out the importance of such factors, stress history and aging, to assess liquefaction behavior. Therefore, this is the basis of the correlation for estimating the cyclic resistance ratio from the horizontal stress index, KD from the MT, because as we noted before, researchers pointed out that KD is sensitive to stress history, including aging, and also to some extent to cementation structure. And also, KD is correlated with the relative density and the in situ state parameter, which are all factors that greatly influence liquefaction resistance. Therefore, KD may be viewed as a cumulative index parameter of liquefaction resistance. It can be used as a proxy of liquefaction resistance. We have seen before, as showing the experimentally the sensitivity of KT to stress history to over consolidation. This is another experimental result which shows the higher sensitivity of KD compared to the compenetration resistance to aging. From experiments carried out by the Yamiolkowski's group on Ticino sand in calibration chamber, in which the sand was pre-strained, applying different pre-straining cycles, which in some way can be viewed as a sort of simulated aging due to the similarity of the mechanism. So in this case, it was found that the increase in KD caused by pre-straining was found to be 3 to 7 times greater than the corresponding increase in penetration resistance, indicated that KD is much more sensitive to aging than the penetration resistance. This is useful information in relation to behavior. So this figure is a summary of several correlations that have been proposed over the years for estimating the cyclic resistance ratio from KD in the framework of the simplified procedure. And it can be noted that the more bold lines are the most recent correlations. The oldest one was proposed by Silvano Marchetti in 1982. The latest one in this figure was proposed by Silvano Marchetti in 2016. And all these curves are referred to as conventional in the simplified procedure to magnitude 7.5 and to clean sand. Now let's talk about the most recent correlations which are included in this figure. In particular, the red one is the more recent, which was developed by Silvano Marchetti in 2016. So there is an increase in research, an increase in interest for this estimating of liquefaction from DMT. The existing curves based on KD were obtained starting from based on CP and SPT, which were converted, translated in some way, or by use of the relative density as intermediate parameters, or by use of direct correlations between the normalized compenetration resistance and KD, depending on the cases. And the attempt was to incorporate the vast experience incorporated methods which are CPT and SPT, because we have seen that there are various reasons for expecting a good estimate of liquefaction based on KD, but so far the field performance data base is limited, so there is the need of further validation. But this method has the potential to be a useful integration to current methods, for example, based on CPT. So more details on the application of these methods will be given by Sara Moroso in the worked examples of this afternoon. But Silvano Marchetti also proposed that even if the DMT can provide potentially good estimates of the cyclic resistance ratio, it could be even better to obtain a prediction based on the same time on KD and the compenetration resistance. Of course, this involves having the results of both kind of tests at the same site. The conceptual framework is explained in this figure and also in this sketch here below, considering that it may happen that if we have two sites which exhibit the same profile of the compenetration resistance, these two sites may exhibit different values of the horizontal stress index, because which reflect, in this case, the higher stress history content of the site 2 compared to site 1. So how to include this information in the estimate of a cyclic resistance ratio? The conceptual framework is to, as a first step, estimate are using common CPT-based correlations, such as Boulanger, Idris, or others. And then, as a second step, adjust these predictions by taking into account the values of KD. Then, if KD is high, increase CRR. If KD is low, reduce CRR. So this qualitative indication that was also translated into a quantitative approach by Silvano Marchetti in using a chart of this type, in which we also see several curves referring to different values of KD. So the use of this chart is that if we know the value of the normalized compenetration resistance, for instance, 100 in this case, and we know the value of the corresponding value of KD equal 5 in this example, we enter in this chart and we obtain values of the cyclic resistance ratio, which is slightly higher than the value obtained by intersection only with this dashed line, which corresponds to the CPT-based estimation. So it is expected that estimate of cyclic resistance ratio based at the same time on two parameters may be better than the estimate obtained from just one parameter, along the line of a multi-parameter, multi-test approach, which is increasingly been used by researchers in the recent years. The most important limitation correlations based on KD is that these correlations are valid only for clean uncemented sand and do not include any correction for the fines contact. This factor, of course, is needs further research. As to the cementation, a possible indication could be obtained by inspecting the profile, the ratio of G naught over MDMT that can be obtained using the DMT, which, similar to the ratio G naught over QC, can provide information also on the cementation. Then, if we use seismic dilatometer, we have the possibility of obtaining routinely pairs of profiles of two parameter shear wave velocity and the horizontal stress index, which are both correlated with liquefaction resistance. So this is a very interesting information, because we can carry out two parallel independent evaluations of the cyclic resistance ratio within the simplified procedure framework. One using the current methods developed based on the shear wave velocity, and the other using the methods Cage listed here. The problem is that we all know maybe that we apply more than one method. At the same side, it is possible that we obtain different predictions. So the concern is which estimate is more reliable. In the case we obtain different estimates from KD and from VS. In principle, of course, this needs further validation, but in principle, we presume that the estimate obtained from KD may be more reliable because shear wave velocity is much less sensitive to KD than KD to stress history, and also that the strains caused by the shear wave are too small to see the effective dilative or contractive behavior of a sand. So this another example obtained that refers to the experience of the Treporti test embankment. In this case, this figure compares the results of parameters, the profiles of parameters obtained before loading and after removal of the embankment. The only difference between these two conditions is the over-consolidation in the removal of the load. So the soil was artificially over-consolidated, and in this case we can see that while the profile of KD clearly shows a large difference between the post-removal and original condition, such difference is only marginally reflected by the comparison of shear wave velocity post-removal and before action. The shear wave velocity is much less sensitive to over-consolidation. So there is other information on this evidence that comes from comparisons of KD and shear wave velocity profiles obtained by SDMT. This is a sand site in Sicily, in which we can see that the KD shows a shallow crust that is believed to be non-liquefiable, which the KD values are higher, but this crust is not felt at all by the profile of the shear wave velocity. So this suggests a lesser ability of the shear wave to velocity to profile liquefiability. This is another case that shows the results of SDMT obtained at the Zelasny-Most tailing dam in Poland, a well-known case presented many times by Mike Jamiorkowski. And in this case, if we look at the values of KD, which are rather low, and the values of BS, which are relatively high, if we apply the methods based on BS and KD to liquefaction, we could found that BS suggests no liquefaction for any earthquake, while liquefaction could be possible based on KD if we are above a certain level of seismic stress. Just the last, I'm going to quickly to the conclusion, just a last slide, which presents a particular case of SDMT results in bonded soils and cemented soils, and these are volcanic soils, in particular in South Italy. And in this case, it may be found that the shear wave velocity may be relatively high because due to the interparticle bonding, which is preserved at small strain, while KD is low because in this case, this bonding is destroyed, at least in part, by the blade penetration. So we should also take into account this condition when we are about bonded soils. So to conclude this presentation, we must stress again that the major distinctive contribution that the DMT can offer in a routine site investigation are information on stress history and on working strain stiffness, plus also the small strain stiffness when using the seismic dilatometer. The sensitivity of DMT to stress history is fundamental in many design applications, starting from the prediction of settlements of shallow foundation, that is number one DMT application that can rely on over 3 decades of good comparison between the measured and DMT predicted settlements. and also the well-founded observation that MDMT is a operative working strain modulus. Also, the use of DMT for compaction control, in particular using the ratio MDMT over QC from before-after DMTs and CPTs, is a suitable approach for evidencing the benefits of ground improvement and also liquefaction assessment. And current trends and ongoing developments of DMT and SDMT research and practice include the increasing application of a multi-parameter, multi-test approach, mostly in the combination with DMT, SDMT, and CPTU results. The increasing interest in deriving in situ decay curves of stiffness versus shear strain from SDMT, and also the validation of methods for liquefaction assessment based on DMT and SDMT. So I have concluded my presentation, and I thank you very much for your attention.
Okay. So thanks, Paula, for your presentation and for being on time. And let's see if there are some questions from the people here in the room or also on the web. I don't know if you can see the chat now. Paula, are you still there? Yeah.
Yes, I'm here. Can you see me?
Yeah. Yes. Yes.
Okay. I'm looking at the chat.
If there are questions, please read, because we don't see the chat at the moment. So.
Okay, I see a question. Is observed settlement for foundations on clay short or long-term settlement that you compare to the MT predicted settlement? The question from Ahmad Sharif. And no, the settlement in clay is the consolidation settlement. So it's a long-term settlement. If we want to distinguish between the unit settlement in the short term and other, we have to make a different evaluation. But generally, the consolidation settlement is the major part of the total settlement, at least in a normally consolidated clay. So basically, we have an agreement, a good agreement by comparing the settlement predicted by DMT using the 1D formulation with the MDMT modulus and the consolidation settlement below a foundation. And
we have a question, Paula, from the audience here.
Yes.
Can we speak? Yeah?
Yes. Yes.
Loud.
Okay. To the microphone.
I can hear you.
I can try this one. I hope you can hear me.
Yes.
You showed us pretty nice that for compaction work, you have you reach an increase in KD at one side. On the other side, a small increase in QC, and consequently, like the ratio of MDMT and QC is increasing. Now, I was wondering now, like if I want to use like the SDMT as a tool for compaction control, would you say, is it possible now for different grain size distributions to define like one specific ratio of MDMT over QC as a quality criteria? Or do you think it's necessary for different test sites where you have different grain size distributions to always define specific site-specific quality criteria?
This is a good question because there are many factors. Can you hear me? Can you hear? Yeah. There are many factors which complicate this matter. One is the difference between the compaction and the ground improvement technique. And one, of course, is the difference of the soil type, in particular the fines content and also the plasticity of the fines content that may make the difference between the different sites. So at this moment, I don't think that we can fix specific numbers that can apply to all conditions, because we have to intersect many different topics. But the trend is very clear. If we look at the previous experience, which have compared different sites, different treatments, we have found in general concordant trends in all cases. So this could be a further step forward to a quantitative assessment of the ground improvement. But now I think that we need a trial check of this at the specific site. So it is better to make some specific check for any test site, for any kind of ground improvement technique.
Yes, please let me add this. I know that Professor Massage is going to give a talk in this conference about compaction and compaction monitoring with the DMT and the CPT. So he will talk about this. 1 month ago, I went with him to Sweden, and we did test before and after vibrocompaction. Of course, it could be very important to do the test before and after, and not only after with M over QC. So seeing the percentage increase of the parameters, in particular of the modulus and KD, that is even better maybe than just the relation M over QC, where even where you have to match two profiles can give some difficulty in the small depth differences. It's possible, but of course, both things can give additional information. So to do the test both before and after the treatment, and then compare also the ratio M over QC.
Thank you very much, because we are really interested in this topic as well, and especially also related to the quality control of embankments. There, we actually are not able to make this comparison of before and after, so we make just the testing after the compaction. And we made a trial embankment, and we made like static and dynamic load tests after each half a meter. And at the end of the head of the dam, we performed SDMD and CPTU tests, and we were able to see that the results of static and dynamic load tests, they really correlate pretty good with KD and ID. So this one was like, we expected a correlation, but this correlation was really, really good. And we are now thinking, like, would it be possible to develop like a general tool or general criteria for quality control also of embankments by using the SDMT? And that this was like the original idea to Paula Monaco, where I wanted to ask this question, because I find this pretty interesting.
Thanks for this suggestion. I don't know, you have published these results already?
Not yet, because we made this embankment like in the summer. Like it was a embankment of about 10-meter height, and based on fine-grained sediments, and we changed like the water content of the material. We stabilized some layers, and yeah, I will show your results later on. Yeah,
look forward, yeah, to see this work. Thank you. Paula, any question online?
No, I don't see any question in the chat.
Okay, so thank you very much for your presentation from remote. And now we will have a lunch break for 1 hour and a half or a bit less, because we will return here at 2 o'clock, right? For Sarah's presentations. So thank you all. Enjoy your lunch break, and we will wait for you at 2 o'clock.
Okay. Bye-bye, everyone. Enjoy your lunch.
Bye-bye. Ciao, Paolo.
Thank you for attending.
Okay. I think it's time to start. So this morning, you saw the first presentation that was given by myself on the equipment, test procedures, and interpretation of the results. Then you saw the presentations from Professor Paolo Monaco, introducing all the applications or most of the applications for which the DMT is used. And now we have Professor Sara Amoroso from the University of Chieti, and she will show you some worked examples on DMT and SDMT, so that you can have an idea of specific methods for the applications that were seen in Paula's presentation. So Sarah, thank you. You have the word now.
Thank you, Diego, and good afternoon to everybody. This presentation will be focused on 3 applications of the seismic dilatometer test: settlement, prediction of settlement, liquefaction, and ground response analysis using DMT and SDMT. So let's start with the settlement prediction. This morning you have seen with Professor Paola Monaco how to calculate the settlement using a DMT test. So using the theory of elasticity, you have this formula where you have the modulus from the constrained modulus from the DMT test every 20 centimeter, and you have the increase of stress induced by the load on the surface. So developing this calculation every 20 centimeter, you can calculate the settlement you develop in depth for each 20 centimeter, and then doing the sum of this equation, you arrive to estimate the total settlement of your subsoil. In particular, how we can develop then the calculation. We need to remember the theory of elasticity, for example, for a circular area or a rectangular area. So looking at this slide, we have here the calculation of the incrementing stress delta sigma z for a circular area. So if you know the geometry of the area, so the radius, and if you know at which depth you want to calculate this incrementing stress, and at which distance you are with respect to the axis of the circular area, you can use this expression. This is a valid expression only under the center of your loaded area, and you can calculate the effective stress until the depth of influence you are considering. So once you have calculated this effective stress delta sigma z, you can enter in this formula using for delta z, so the increment in depth, the value of 0.2 meter, and using the constrained modulus corresponding to the same depth, you repeat this calculation for each DMT measurement, and you arrive to the calculation of the settlement. Outside the outside the center of the loaded area, we have some chart that were developed by Poulos and Davis, where entering with the ratio R like distance from the center of the loaded area and R that is the radius of the loaded area, and selecting the depth indicated by this ratio Z, that is the depth, and there is again the radius of the loaded area, you can select wherever you want to calculate the increment in stress. As you can see, this increment decrease with the depth and with the distance from the center of the loaded area. Similar consideration can be done if we change the shape of the loaded area. These are all formula from the theory of elasticity. So I show you another shape of loaded area, that is the rectangular area. In this second case, the delta sigma z is calculated under the corner of the loaded area. So this formula is valid only if you are in one of the corners of the rectangle. As you can see, also in this case, this formula is a function of the load and is a function of the geometry of the loaded area, where you have the length and the width of your foundation, and then is a function also of the location of the point where you want to calculate the load, so R1, R2, and R3. Then the primary settlement is again evaluated with the same formula. So just to give you an example of what means what I anticipated with the other slide, is that if we have a point in the middle of the rectangular loaded area, we have to subdivide our big rectangle in 4 smaller rectangles that have a corner in common, considering 1, 2, 3, and 4. So all these 4 rectangles represent area that are loaded, but the sides of your rectangle are, for example, for rectangle number 1, are A first, M. Or if you have to calculate the load of the second rectangle, the 2 sides of the rectangle will be A first, B first, and the same for the other situation. So at the end, the total load that you calculate for this point that is inside the loaded area is the sum of the 4th rectangles. If the point is external to the loaded area, we can still calculate the increment in stress generated even in a point at a certain distance from the loaded area, that is A, B, C, D. So in this case, we have the same consideration that all the rectangle where we calculate the load, the settlement, sorry, should have a corner in the point M. So we will have a big rectangle, A, B first, M, C first. And then we have to subtract the area that are not loaded. So one rectangle is C, D first, M and C first. And the second rectangle is B first, M and D second. But subtracting these two bigger rectangles, we have subtracted twice this smaller rectangle. So we have to sum again the increment in stress induced by the rectangle D first, M and D second. There are also other possibility to calculate the increment in stress induced by a rectangular loaded area. For example, you have this chart from Steinbrenner, and where you enter again with the size of your rectangle and with the load. This chart has also a zoom for the value of this part that could be not readable if you are trying to estimate the increment in stress in this part of the chart. And on the other side, you can also have a value in a table where you can interpolate the value that you are interested to know. If we go now to see how to move with a real exercise with numbers, we can refer to this case study in Columbia in 2015, where a seismic dilatometer test was performed. This is a deposit of clay. You can see here from the material index that the profile of this subsoil is quite homogeneous, below the 3 or 4 meter depth, and you can see the same profile also for the modulus, except in at a depth of about 26 meters, where you can see a small increment of the modulus that is, however, below 8 MPa, so very soft material. Here you can find also the other parameter, so the undrained shear strength, KD, and shear wave velocity. For this exercise, we will focus, as you can imagine, only on the use of the constrained modulus. We also developed the profile of the other parameters, so the OCR or the K-naught, where you can see that the material is normally consolidated. So if we try to now to use the data of this soil profile, considering a circular area with a diameter of 30 meters, and considering a load of 30 kPa that are applied at a depth of 2 meters, we can try to calculate the settlement induced by this load. So we remember that is a circular area, so we have to estimate the increment in stress delta sigma z using the formula we have seen before. And therefore, we can try easily to implement an Excel file where we know the geometry. So we know that the radius is 15 meters, the load is 30 kPa, and the depth of application of the load is 2 meters. And therefore, by using the DMT data that are the depth, the unit weight, the effective vertical stress, the pure water pressure, and the modulus, and in red on the right side of this Excel file, we have calculated the parameters necessary for the theory of elasticity to calculate the increment in stress delta sigma and then of the settlement. So the total settlement is 276 millimeter. That, as you can see, has been calculated every 20 centimeter since we have the modulus every 20 centimeters. Therefore, we repeated the same exercise, but changing the shape of the loaded area. So in this case, we consider an area with a size of B equal to 15 meters and L equal to 30 meters. And we maintain the same load and the same depth for the foundation. So in this case, we have seen that we can try to estimate the settlement not only under the center, but also under the corner and under other points of this loaded area. So let's start with remembering the formula that we have seen in a few slides before. So we have to implement this formula, delta sigma z, as a function of the load and of the geometry and of the depth of interest. And therefore, we can implement another Excel file. So the empty test result that you can see on the left are the same of the previous exercise, because we are in the same subsoil and so never changed. For the geometry, if we are under the center of the rectangular area, we have to divide this rectangle in 4 rectangles that have a corner in common. So in this case, we can subdivide the area in 4 rectangles of the size of 15 meters and 7.5 meters. So at the end, when you go to calculate the settlement for one of these rectangle, you have simply to multiply by 4 the final settlement that you have obtained. So settlement under considering one rectangle is 56.75 millimeter, and then multiplying by 4 we obtain 227 millimeters. If we consider a corner of the rectangle, the situation is simpler, because we don't have to subdivide in rectangle our loaded area, but we simply consider the single rectangle with sides of 30 meters and 15 meters. Same procedure, so in this case we obtain a settlement of 80 millimeters. So you can see already the difference considering what happens under the center of the loaded area and under a corner of the loaded area. Finally, other 2 cases, which is the settlement under the median point of the short side. So in this case, we need to subdivide in the 2 rectangles of the same size the area. And the settlement in this case is given by the product of 61, that is the settlement of one of these rectangles for 2 millimeters. So the total settlement is 122 millimeters. So it's very simple to implement this Excel file. Same procedure for the other side of the rectangle. So if we are in the median point of the long side, easily we can change the geometry here that consider two rectangle 50 meter for 50 meters. And we obtain a settlement of 73 millimeter for one of the two rectangle, and then multiplying by 2, we obtain a final settlement of 146 millimeters. At this point that we have understood how to arrive to the calculation of the settlement, you should know that there is also a software, DMT settlement, that can do this calculation automatically. So this software can be downloaded from the Marchetti DMT website. And once downloaded this software, you can open it and you can find a manual where you can find information on the use of the software. So it's very easy to go through and find the information you need. So let's go to repeat the same calculation using the software, just to have an idea on how the software works. Going back to the circular area, in the software we have the first window when we can select the type of loaded area, so if it's isolated or multiple loaded area, and you can select the shape between square, rectangle, or circle. And as a function of your selection, you have different information to introduce here. In particular, you can include the diameter, the load, and automatically the total vertical load is calculated, and the depth of the application of the load. And as long as you change these numbers, this section and plan are updated. Second step is to import the DMT data. So you can import a DMT unifile that is possible to export from the SDMT software that you use for the elaboration of DMT data. So you can import this file, and automatically you will see these 3 columns with depth, constrained modulus, and effective vertical stress, together with the information about the test site. So these are imported automatically using this format of this file. Next step is if we want to assign some limits in the calculation of the settlement, limits for the lower value of the modulus that we want to consider for the settlement, or limits in the end of the calculation if is the last depth of your profile, or if you consider negligible settlement below a certain ratio, delta sigma over sigma first. And another information to add is the thickness of the layer where we want to calculate the incremental settlement. So if the test is 20 centimeter, I will say that this value should be 20 centimeter. At this point, the software automatically do the calculation, and you can see the result under the center and under the edge of your loaded area. And you can see that these values are the same that we have obtained with the Excel file. The good point of the software is that the software automatically produces a report and automatically produces this graph. So you can see together the profile of the constrained modulus, the vertical stress increment that, as you can see, decrease with the depth. The vertical strain epsilon, so this is very important graph, because from this graph you can check which are the layer that settle more, and this look to happen between 6 and roughly 18 meters. And then you have the calculation of the total settlement. So you can find this graph. We can repeat the same calculation even for a rectangular area. So the procedure is the same. We only change the information on the side of your rectangle. You import again the test, and you select your calculation option. So same thing of previous case. And at the end, you arrive to have again this calculation under the center, under the corner, and in the median point of your loaded area. Finally, also in this case, you can have, together with the constrained modulus, the vertical stress increment, the vertical strain, and the total settlement plot. So this is the end of the first part. I don't know if maybe we can have a question at the end of this 3 section of presentation, and we can move to the second part that is on ground response analysis. So the second part is on the ground response analysis, because as you have seen this morning with the seismic dilatometer test, you can calculate a profile of, you can measure a profile of the shear wave velocity, and you can estimate a profile of the G over G naught decay curves. And these two information are very important for ground response analysis, because as you can probably already know, when you perform a ground response analysis, you have different information to input in a software. Let's say a 1D software, for example, that is easier. So you have an input motion that is the earthquake at the bedrock level. Then you need to know which is your soil stratigraphy. And together with your soil stratigraphy until the bedrock depth, you need also to know the shear wave velocity profile and the nonlinear behavior of the soil. So all these three information are used then to obtain an output motion in terms of acceleration, spectrum, or other parameter that are helpful for seismic design. And here I put a list of all this information, and in particular about the information that you need from the geotechnical characterization for the performance of a ground response analysis. One information is the unit weight of the soil layer and of the bedrock. Then we have the shear wave velocity of the layer and the shear wave velocity of the bedrock. Then, if we are performing 2D response analysis, we need the Poisson coefficient and the compression wave BP. And then we need normalized stiffness decay curves, so G over G naught as a function of the shear strain, and the damping curve, so D as a function of shear strain. So if we think about data that the seismic dilatometer can provide, we have for sure the soil unit weight and the shear wave velocity, and a reasonable estimation of the stiffness decay curves. So here, just to remember which are the formula that we can use for from the DMT test, and in particular for the unit weight, we have the Marchetti and Krabs chart that is here reported, and where you can enter easily using the material index ID and the dilatometer modulus ID. So if we do an example, when we have ID equal to 1.6 and dilatometer modulus equal to 200, we can define a soil classified as a sandy silt that has a unit weight of 1.8 times the unit weight of the water. So let's say approximately 18 kilonewton for meters cube. And therefore, from the value of the unit weight, we can estimate the effective vertical stress. Here I reported an example of result from seismic dilatometer test, where together with the DMT parameter, now you can see also the shear wave velocity profile. That is an important parameter for the development of ground response analysis. And the other point that we need to consider for ground response analysis is the estimation of stiffness decay curves. So you have seen today, this morning, with Professor Paola Monaco, how to develop this curve. And this curve substantially need to know the constrained modulus from the DMT test that is used through the theory of elasticity to calculate the operative shear modulus GDMT, as a function of MDMT, so the constrained modulus, multiplied by a ratio that is a function of the Poisson coefficient. So using several data points from several research sites in the world, we reached this formulation that is an hyperbolic equation that is a function of G naught and GDMT and the shear strain for DMT test. So this equation can be used as an estimation of stiffness decay curves. So if we have a profile of a seismic DMT test, we can estimate GDMT from the theory of elasticity, as we have seen in the previous slide, so as a function of constrained modulus and Poisson coefficient. G naught from the shear wave velocity, again using the theory of elasticity. And then we have the shear strain for DMT test that has been estimated in different range, considering if we are in silty or clay material, or if we are in sandy soil. So this range, as you can see in this slide, are lower for sandy material, so between 0.015 and 0.30%, and a little higher for silt and clay, so between 0.23 and 1.75. So as much the material are softer, as much this shear strain move on the right side. This equation has been recognized as a reasonable approximation of cyclic or dynamic result, as can be observed by overlaying the result from laboratory test and the estimation of the curve using the hyperbolic equation. Anyway, we are still collecting other data from other research sites to further validate this equation. So let's go to see also in this case an example to verify how to use the seismic dilatometer test for ground response analysis. In this case, we used the result of a test site in Italy, in Arpino, central Italy, where we performed a deep investigation using seismic dilatometer test, boreholes, downhole testing, and CPT test. Here you can see the plot of the data collected from this test site, where you can see a profile that is changeable between silt and clay material until 22 meter depth, where the test ended because we reached the maximum resistance for the penetrometer. We have a quite homogeneous profile of the constrained modulus between 9 and 22 meter, while in the upper part we have some variability. And you can see also we have a complete profile of the shear wave velocity until that depth. We also did a comparison with the downhole test that was performed by University of Florence that reached deeper layer because we had a boreal until 70 meters of depth. So you can see that between 6 and 22-23 meters, we have quite a good agreement between downhole and seismic dilatometer test. So by looking at the stratigraphy and by looking at the seismic DMT test, we divided the subsoil in a number of geotechnical units until the bedrock layer that was reached at 171 meter depth. So we detected a layer between 0 and 2.5 meter of silty of clayey silt and sandy silt. Then another layer between 2.5 and 3.9 of silty clay. And then a third layer until 5.6 of silty clay and silt. And again, another layer, material 4 until 11 meter of silt, clayey silt and sandy silt. And then a thicker layer that was this layer that we detected clearly looking at the DMT profile between 11 and 22.6. After this layer, we found a gravel material for a few meters, and then we enter in the stiff clays that started at 24 meters and arrive until the seismic bedrock. So in this case, by looking at the available data that are data from SDMT, downhole and laboratory testing, we tried to perform a seismic response analysis. So the first problem is to have all the geotechnical parameters necessary for this subsoil characterization to be included into a 1D software like Strata, for example. Other information that we have would help in the estimation of the damping curves that are not produced by the DMT test. And then we have some information on the two geotechnical units, material 6, material 7, and also the bedrock that where the seismic dilatometer test didn't arrive in depth. And finally, we have also an assumption for the damping of the seismic bedrock. Together with this information, we also have from literature a curve from material 6 that I remember is gravel layer. While for material 7, we have result from laboratory test that are here plotted in the blue color. For these two material, the shear wave velocity value are produced using downhole test. So you can see here the value of the shear wave velocity that we have from the downhole test. For sure, we also need to select a seismic input that in the case of Arpino was considered for an earthquake of magnitude 6 according to the national building, the Italian building code. And now how we can use the dilatometer information to estimate the geotechnical model into the first 5 units that until 22 meters of depth. So the shear wave velocity is very easy because it's a measurement that is produced from the in-situ test, while the point is to estimate the decay curves. So G0 formula is a function of the density and is a function of shear wave velocity, so we can easily calculate G0. Then constrained modulus is a direct parameter from the DMT test, and therefore we can calculate this parameter. And then through the theory of elasticity, we can move from the constrained modulus MDMT to the operative shear modulus GDMT, assuming a value for the Poisson ratio, generally equal to 0.2, 0.3. And last step is to select a value for the shear strain for the DMT test according to the soil type. So if it's a sand, if it's a silt or clay, or if it's a soft clay. The other point is that we need also to estimate damping curves, because this curve is the other input to provide the information on the nonlinear behavior of the soil. So if we assume to use literal reference curves, like Darendelli and Stock curve, we can estimate the effective vertical stress using the unit weight from the DMT, and therefore we calculate the effective vertical stress. And then, considering that we have only cohesive soil, we can calculate the over-consolidation ratio using the DMT formula. That is a function of the horizontal stress index. In the case of sandy material, we can combine the information from the DMT, so the constrained modulus, with the corrected con resistance from CPT test. And finally, the other input for this damping curve is the plasticity index that has been provided in the input data of the exercise. So at this point, we can calculate these parameters for the 5 geotechnical units that are between 0 and 22 meters of depth. So we can do inside the each layer the average of the parameter that the DMT test provide. For example, for the unit weight, for the effective vertical stress, for the OCR, and for all the other parameters. And in this way, we have all the input information necessary to build the stiffness decay curves and the damping curves for our geotechnical model. Here are reported the input information that we need before starting the calculation. So the shear wave velocity profile until the bedrock located at 171 meters. The stiffness decay curves that we have developed for the 7th geotechnical unit that we have, so 5 from the seismic dilatometer test and the other 2, 1 from laboratory test and 1 from reference. And then this is, for example, one of the output of our calculation. So usually the spectrum profile as a function of the period is one of the most interesting information for engineering design. And here you can see the plot of the 5 accelerometer that we used as input, and the average value of these 5 output response spectra. This 1D software provide you also the profile of the acceleration with the depth, for example, or of the shear strain with the depth, or of the shear stress. So here you can find this different plot for each seismic input, and the red line represent the output for the average. So now we can move to the last part that regard the last application, that is the liquefaction assessment. So to move through the topic of liquefaction, I thought to show you an example of liquefaction calculation that we have performed together with Professor Paola Monaco for the Emilia-Romagna area, where an earthquake affected the area in 2012, and general liquefaction phenomena were developed in some villages of this region. In particular, the village of San Carlo was one of the most affected by this phenomena, and therefore several projects were developed here to estimate liquefaction potential of the area. Here you can see a map of all the investigations that were performed, and in particular we performed also 4 seismic dilatometer tests that in correspondence of liquefaction evidences. This data show us that there are sandy material in the upper 10 meters, and then we move into a clay deposit before going back into the bottom layer of sand that belongs to the Po River. If we go to see the result of the sea reading that we have acquired at these 4 sites that are located in a different part of the village, we can observe that generally we can detect 2 different groundwater levels that are clearly detected by 3 of this seismic dilatometer test, while 1 has measurement only in the 2nd groundwater level. And this is an important information because this allowed us to have a groundwater profile that account for both the groundwater level, also into the elaboration of DMT data and in the elaboration of liquefaction assessment. At the same sites, we also had measurement of CPT and seismic CPT. In particular, if we look at one of these seismic dilatometer profile, where we can see these 2 sandy layers disconnected by this aquiclude of clay material, we can observe in terms of shear wave velocity that we have a good agreement between seismic CPT and seismic DMT. Moreover, since this was a huge research site, we also have some measurement with the Bender elements. And we can see that also the measurement with the Bender element fit very well with DMT, seismic DMT test. These are the result of the CPT test. So even in this case, we can observe with except for the first 2 meter depth, a silty sandy material, then the clay layer, and then again another sandy layer. So the first thing that we went to look, considering also the Italian building code, is if having this kind of result, we have to perform liquefaction analysis according to the building code or not. In Italy, we have some particular case where we can avoid to perform liquefaction analysis if we are in one of the 4th condition that you can read below. So one of these conditions is to have a peak ground acceleration below 0.1 g. Or another condition is to have a groundwater level bigger than 15 meters. So in absence of water, it's difficult to have liquefaction. Or if you have SPT profile or CPT profile, if the corrected SPT or CPT parameter are respectively bigger than 30 or 180, you can avoid to perform liquefaction analysis. Or last condition is if you have your deposits outside the zones that are indicated in the grain size curves, you can avoid to perform liquefaction analysis. So the first thing we tried to verify is if we were in one of these 4th condition. To do this, considering if we are doing a design project, we have to refer to which are the acceleration at the ground surface that we have for our site. So we refer to national standard, considering that we have a map in Italy of 1 kilometer for 1 kilometer, where we have indication of acceleration at the bedrock level, and simply introducing the coordinates, latitude and longitude, we can arrive to the estimation of the PGA. So, including this value of coordinates, we arrive to a peak ground acceleration at the bedrock level for a return time of 475 years, equal to 0.152 G. So this value is already bigger than the prescription of Italian building code. Then we should amplify for the soil category. So considering the shear wave velocity profile usually in the upper 30 meter of depth, we can estimate which is the subsoil category. So by considering that we have seismic dilatometer profile and a seismic piezocon profile, we can estimate the soil category. The soil category for this profile is category C, because our equivalent shear wave velocity is approximately 185 meters per second. At this point, we can move from the PGA at the bedrock level to the PGA at the ground surface. So by considering that our topography is flat, so we don't need to amplify the PGA for the topography, and by considering that our soil category is C, we have a coefficient S sub S equal to 1.464. So multiplying the PGA at the bedrock level for this subsoil coefficient, we arrive to a PGA at the ground surface that is 0.222 G. So the first suggested by the building code is not respected. Second condition was related to the groundwater level, but also in this case we didn't respect the condition because the groundwater table is above 15 meter depth, and this is provided using DMT readings. Third condition is to consider if the QC1N, so the corrected cone resistance, normalized cone resistance, is below 180. And even in this case, is above 180. And in this case, it is always below 180. So we cannot exclude that liquefaction can happen. Last condition is to verify if we are outside the grain size zone. The grain-size zone are this red and green line reported here for uniform on the right and non-uniform soil. So using laboratory test result, once estimated also the uniformity coefficient, we plot the curves into this zone, and we noted that are perfectly inside the liquefiable area. Therefore, there is no way to avoid to perform this liquefaction analysis. And at this point, we have to think how to perform this calculation using CPT and DMT data. If we remember that for liquefaction analysis, we need to estimate a safety factor to liquefaction that is given by the ratio between the cyclic resistance ratio, that is a function of one of the in-situ tests, and the cyclic stress ratio, that is a function of the earthquake. We can try to move through this calculation. So for our case study, we have the information about the PGA that we have already calculated to be equal to 0.222 G. But we need the information of the magnitude of the earthquake that we need to correct the cyclic stress ratio through the moment magnitude factor to arrive to the cyclic stress ratio that we need to include into liquefaction analysis. The other parameter that you need for the calculation of the CSR are provided if we know the total and the effective vertical stress, and this coefficient that is a function of the depth. So, first point is to estimate the magnitude, and for a design approach, as we are doing for this example, we can think to use the moment magnitude provided for the case of this site in Italy, using the classification into the seismogenetic zone. So considering geological aspect, fault, and other factors that influence the seismicity of Italian territory, Italy has been divided into seismogenetic zones, each one is characterized by a different magnitude. So this zone is characterized by a moment magnitude equal to 6.14. That is similar to the magnitude that we have in 2012. So next step is if we know how to calculate the CSR, we need to know how to calculate the CRR. We have a different formula, so you probably already know the formula from CPT, that is a function, for example, if we use the Idriss and Boulanger 2008 approach, is a function of the normalized corrected tip resistance. And okay, so So by considering the data set that we have for our case study, we can start to see which are the formula for the CPT and then which are the formula for the DMT. For the CPT, if we use the Idriss and Boulanger 2008 profile, we can see that for the calculation of the CRR, that is the other parameter that we need for the safety factor calculation, we can see that QC1N CS, so the normalized corrected tip resistance for clean sand, is the parameter that we need to calculate. So this parameter is calculated with an iterative procedure that include the measured con resistance. And include also the percent of the fines content into the formula. And into this approach, Idriss and Boulanger, to calculate the CSR, for which we have already seen the formula in one of the previous slides, these two authors have a particular formula for the magnitude scaling factor that is here reported, and is important to know because we will see that each author usually have a different coefficient to estimate this magnitude scaling factor, but also to estimate, for example, the corrective coefficient for the effective vertical stress, K sigma, or to estimate RD, that is a correction related to the depth. We will use some of these parameters also for the DMT calculation of the cyclic stress ratio. So you can find here all the formula. For the CPT, another method that is again a function of QC1NCS, but the definition of QC1NCS is a little different from the procedure of 2008 because you can see that the correction for the fines content, as you can see in this formula, is a little different. Moreover, you have some differences also in the calculation of the magnitude scaling factor that in this second case is a function of the corrected tip resistance for clean sand. Moving to seismic dilatometer test, as Professor Paola Monaco already showed you this morning, we have different equation, different methods developed by different authors. This CRR chart were developed for a moment magnitude equal to 7.5 and for clean sand. So we don't have at the moment a correction for the fines content. Here I report only the equation of the different method that you have already discussed this morning. So we have the Monaco et al. 2005 equation developed for as a function of KD. Then we have another equation developed by Tsai et al. 2009. That is a function of KD. And finally, we have the Marchetti method that is a
Well, probably there is a connection problem from Italy. I think we are very close to the end of the liquefaction example that Sarah Amoroso wanted to do. I would like to thank all of you for attending the course. I hope it was interesting for you and helpful. The aim was to give you an idea of the instrumentation, of the testing procedures, the equipment and applications, and with this last Sarah's test, some examples of real case projects and very practical exercises that may be similar to applications that you could find in your profession. So I think she will not connect, and maybe we can have our break that we skipped, and in case she will connect, we can take a look with a coffee in our hands. We will be at the conference, myself, and probably also Sarah and Paola by remote. We will have a stand here. If you want to talk about what you have heard today, just come over confidentially. We are available, of course. And thank you very much. Bye.